What if the most important ships in human history haven't been built yet? Not the vessels that crossed oceans, nor the rockets that reached the moon, but the freighters that will one day sail between stars, carrying the very lifeblood of civilization across unimaginable distances. For thousands of years, trade routes have defined our world. The Silk Road connecting east and west, shipping lanes crossing oceans, and now the digital highways moving information at light speed. But what comes next may dwarf them all, transforming humanity from a single world species to a truly galactic civilization. The key lies in something we often take for granted: the movement of goods, resources, and materials across the void of space. This is the story of interstellar freight and how it could become the foundation of our first economy spanning multiple star systems. Picture this: enormous vessels gliding silently through the darkness between stars, their holds filled with rare minerals from alien worlds, manufactured components from orbital factories, and perhaps even living organisms destined for new habitats. These wouldn't be the warships of science fiction, but the merchant marine of the cosmos, the workhorses that make interstellar civilization possible. They would represent the culmination of countless technological breakthroughs, from revolutionary propulsion systems that make crossing light years feasible, to sophisticated logistics networks that can manage supply chains across unimaginable distances and time delays. The challenges are staggering, but so too are the potential rewards: access to resources beyond our wildest dreams, new frontiers for human settlement, and an economic system that literally spans the galaxy. What makes this vision particularly compelling is that we're already laying the groundwork here on Earth and in our own solar system. Private companies are developing reusable rockets, nations are planning lunar bases and Mars missions, and researchers are experimenting with technologies that could one day power starships. The step from interplanetary to interstellar trade may seem enormous, but history shows that where commerce leads, civilization follows. In this exploration, we'll uncover how humanity might build this incredible future, examining the technological innovations, economic models, and human factors that could turn interstellar freight from dream into reality. This journey isn't just about speculation. It's about understanding the next great chapter in human expansion and how the humble cargo ship might become our passport to the stars. The massive vessel glides out of the high-orbit space dock with a silence that belies its incredible power. Its silhouette is not sleek like the starships of cinema, but blocky and utilitarian, a series of modular containers locked into a spine-like frame stretching over a kilometer long. At its stern, the faint, mesmerizing glow of contained antimatter annihilation provides the thrust that will push it across the 40 trillion kilometer void to Proxima Centauri. This isn't a vessel of exploration or conquest. It's the SS Merchant's Hope, a bulk freighter, and its departure from the Martian transfer station marks the single most important economic transaction in human history. Its cargo hold doesn't contain colonists or soldiers, but something far more valuable: 20 tons of refined platinum group metals mined from the asteroid belt, a sealed container of genetically engineered algae designed to terraform a new world's atmosphere, and a diamond solid data chip storing the entirety of a nascent alien world's first decade of geological and biological survey data. This is the dawn of interstellar trade, and it begins not with a flag but with a bill of lading. This monumental shift represents the next logical step in a chain of economic expansion that has defined our species for millennia. We progressed from carrying goods on our backs along footpaths to loading wagons for overland routes like the Silk Road, to building massive container ships that now crisscross our oceans. Each leap in transport capability unlocked new resources, new markets, and new levels of civilization. Interstellar freight is simply that same principle scaled to its ultimate expression. As leading astroeconomist Dr. Lena Petrova often notes, the economics are brutally clear. Sending automated freighters ahead of human settlers eliminates the immense life support costs and ethical dilemmas of transporting fragile human bodies. A freighter doesn't need food, water, oxygen, or gravity for years on end. It can tolerate higher radiation levels and acceleration forces. Most importantly, it can be designed for a one-way trip if the economics support it, becoming a permanent asset in the destination system. The profit potential from moving incredibly high-value, low-mass goods between stars makes this endeavor not just possible, but, for certain cargoes, inevitable long before faster-than-light travel is even a theoretical possibility. So what exactly would be valuable enough to justify the astronomical cost of shipping it between stars? The answer lies in things that are uniquely valuable at the point of destination. Data is the prime example. The information gathered by a robotic survey mission about a planet's ecosystem, mineral deposits, and weather patterns is nearly massless but unimaginably precious to the first colonists arriving decades later. Then there are biological samples, seeds, microbes, and genetic material from Earth or other settled worlds that could be used to kickstart agriculture or bioremediation on a new planet, saving centuries of adaptation. Certain rare isotopes or exotic materials with unique properties, perhaps only created in the heart of a supernova and thus incredibly scarce in our solar system, could be worth their weight in antimatter to a cutting-edge research facility light years away. And we cannot discount manufactured goods either. A single, perfectly fabricated computer chip or fusion reactor component, impossible to replicate with a new colony's fledgling industry, could be worth shipping across the light years to keep a critical system online. This is the bedrock of the first interstellar economy, not bulk ore but specialized, irreplaceable value. This foundational shift redefines our very concept of wealth and power. Throughout history, control of trade routes has consistently created the world's wealthiest and most influential individuals and empires. The merchant princes of Venice, the spice traders of the Dutch East India Company, the railroad and shipping magnates of the industrial age, their fortunes were built on moving goods from where they were abundant to where they were desired. The first trillionaires of the Galactic era will likely follow this exact same blueprint, but on an unimaginable scale. They will be the owners of the freight lines, the controllers of the logistics networks that manage the complex ballet of launches, transfers, and arrivals across years of travel time and light years of distance. They won't be explorers planting flags, but the indispensable intermediaries without which interstellar civilization simply cannot function. Their decisions will determine which colonies thrive and which struggle, shaping the political and social landscape of humanity's future among the stars. This is the quiet, practical, and profoundly powerful revolution that begins not with a dramatic first small step, but with the first profitable delivery. The sheer scale of interstellar distance makes propulsion the single greatest engineering challenge, and the solution will likely come from physics that once belonged only in theoretical papers. While chemical rockets got us to the moon and ion thrusters are perfect for nudging satellites, crossing the light years demands a power source of an entirely different magnitude. The most promising candidate for the first generation of these star freighters is nuclear fusion. Imagine harnessing the same process that powers our sun, contained within a magnetic bottle at the stern of a ship. A fusion-driven engine would work by superheating a propellant like hydrogen into a plasma, and then ejecting it out of a magnetic nozzle at a significant fraction of light speed. This provides a continuous, efficient thrust that could, over years, accelerate a massive vessel to cruising speeds that would make a journey to a nearby star like Proxima Centauri a matter of decades rather than tens of thousands of years. The beauty of fusion is its fuel source. The primary fuel, deuterium, can be extracted from seawater here on Earth, while its potent partner, helium-3, could be mined in vast quantities from the lunar surface or the atmospheres of gas giants, turning our solar system into the fueling depot for the galactic economy. But for those who dream of even faster transit times, the pursuit leads to an even more exotic and efficient power source, antimatter. The complete annihilation of matter and antimatter releases energy with 100% efficiency, a figure no other reaction can match. Just a few grams of antimatter could theoretically provide enough energy to propel a ship to another star system. The challenge, of course, is monumental. Creating antimatter requires immense particle accelerators, and storing it requires incredibly complex electromagnetic traps to prevent it from touching any ordinary matter and violently exploding. Yet the potential payoff is so staggering that research continues. An antimatter-initiated fusion engine or even a pure antimatter rocket could slash interstellar travel times to mere years, transforming the economic calculus entirely. A journey that takes 50 years is a one-way investment for an automated freighter, but a journey that takes 5 years opens up the possibility of a viable round-trip trade route, fundamentally changing the relationship between star systems. Then there are the concepts that push at the very boundaries of known physics, the true game changers that could rewrite the rules entirely. The most famous of these is the Alcubierre warp drive, a theoretical model that proposes contracting space-time in front of a ship and expanding it behind, effectively creating a bubble where the ship itself remains stationary while moving faster than light relative to the outside universe. While the energy requirements were once thought to be astronomically impossible, equivalent to the mass energy of Jupiter, more recent mathematical refinements have suggested ways to reduce that need to something more conceivable. If such a drive could ever be realized, it wouldn't just enable interstellar freight. It would create an interstellar internet where data and high-value goods could move between stars almost as easily as they move between continents today. This isn't just about moving faster, it's about redefining distance itself. These aren't merely thought experiments. The foundations for these technologies are being laid right now. NASA's Innovative Advanced Concepts program consistently funds early-stage research into propulsion systems that sound like science fiction, from fusion-driven rockets to designs that harness the quantum vacuum. In the private sector, companies like SpaceX have fundamentally changed the economics of space access, proving that relentless innovation and a commercial focus can dramatically accelerate progress. Their work on massive, fully reusable launch systems is the necessary first step to building the orbital infrastructure where these future star freighters will be assembled. This work builds on visionary studies from the past, like the British Interplanetary Society's Project Daedalus from the 1970s. Daedalus was a detailed engineering study for an unmanned, fusion-powered interstellar probe, and it remains a surprisingly relevant blueprint, outlining the challenges of engine design, shielding, and long-duration autonomous operation that any future freighter must solve. The propulsion system itself is only part of the equation. The true test is endurance. How does an engine, especially something as complex as a fusion reactor, operate flawlessly for 50 years without any possibility of physical maintenance? The answer lies in incredible redundancy, self-repairing systems, and advanced artificial intelligence. The ship's AI would be more than just a navigator. It would be a chief engineer, constantly monitoring millions of data points, predicting failures before they happen, and managing swarms of robotic repair drones that can fabricate replacement parts from raw materials stored on board. The cargo itself would need to be protected by sophisticated magnetic shields to deflect cosmic radiation and layers of Whipple shielding to absorb the impact of micrometeoroids flying at relativistic speeds. Every component, from the largest engine coil to the smallest data processor, would have to be radiation hardened and built to a standard of reliability we can barely imagine today, because a breakdown halfway to Proxima Centauri is a permanent economic loss. This relentless focus on durability and autonomy is what will turn a brilliant propulsion concept into a trustworthy truck of the stars. This economic framework forces us to think about value in a completely new way, divorced from the familiar markets of Earth. The foundational principle is brutally simple. For any good to be worth shipping across light years, its value per kilogram at the destination must be astronomically high enough to cover the even more astronomical cost of its delivery. This immediately rules out bulk commodities like raw ore or basic construction materials. No one is going to pay to ship steel or concrete 4.37 light years to Proxima Centauri b when they can almost certainly mine and manufacture it locally. Instead, the first interstellar manifests will read like a catalogue of the unique, the irreplaceable, and the incredibly information-dense. Think of specialized medical supplies tailored to the specific genetic profile of a founding colony, or a single master seed bank containing millions of Earth crop varietals, its value measured in the long-term food security of an entire world. Consider a compact industrial replicator, a machine that can build other machines, sent to jumpstart a colony's entire manufacturing base. These are the goods that found civilizations. Dr. Aris Thorne's research highlights a fascinating dynamic he terms asymmetric scarcity. This is the engine that will drive interstellar commerce. It's not just that something is rare, it's that it is uniquely rare in one system while being potentially abundant in another. A pristine, Earth-like exoplanet might have vast, easily accessible deposits of platinum group metals, making them a common industrial material there, while Earth's own reserves are depleted and incredibly expensive to mine. Conversely, that young exoplanet might lack the complex biochemical diversity that 4 billion years of evolution produced on Earth, making a single gram of engineered soil bacteria from our world worth a fortune for its terraforming potential. The profit isn't just in the material itself, but in the information and utility it contains relative to its new environment. This transforms a freighter from a simple transporter into a kind of temporal arbitrageur, betting that the value differential between two star systems separated by decades of travel time will remain high enough to turn a profit upon arrival. The financial structure supporting such a venture would be as complex and unprecedented as the technology itself. The initial capital outlay for building a single interstellar freighter would be colossal, likely requiring consortiums of corporations or even planetary governments, similar to how major infrastructure projects are funded today. Given the decades-long round-trip time for even the nearest stars, this becomes a multi-generational investment. Investors who finance the launch of the Merchant's Hope cannot expect a return on their capital within their lifetimes. They are investing in a legacy, a trust fund for their grandchildren's generation. This necessitates entirely new financial instruments, long-duration bonds spanning centuries, futures contracts that account for relativistic time dilation, and incredibly sophisticated insurance models underwriting against a universe of risks, asteroid impacts, coronal mass ejections from unknown stars, or even the existential risk that the destination colony might fail before the ship arrives. The very concept of interest and ROI would have to be re-engineered for a timescale that dwarfs human lifespans. We can look to history for a powerful analogy: the spice trade of the 16th and 17th centuries. A merchant in Amsterdam would finance a voyage to the East Indies, an endeavor that took years and carried immense risk from storms, pirates, and disease. The cargo of peppercorns, nutmeg, and cloves was, by weight, worth a fortune in Europe precisely because it was scarce and difficult to obtain. The journey was so long and uncertain that the market conditions upon the ship's return were a gamble. Interstellar trade operates on the same principles, but the distances are millions of times greater, and the travel times are decades instead of years. The freighter crews, or more likely the autonomous AI agents managing the trade, become the new Dutch East India Company, leveraging information asymmetry and accepting incredible risk for the promise of even more incredible reward. The ones who can most accurately predict the needs of a colony 40 years in the future will be the ones who build the first galactic fortunes. This leads to a profound shift in the very nature of wealth and power. The owners of the freight lines, the entities that control the conduits between stars, will wield influence unlike any corporation in history. They won't just move goods, they will dictate the viability of off-world colonies, shape the cultural exchange between stellar societies by deciding what information and art is transported, and essentially become the circulatory system of galactic civilization. A delay in a shipment of critical medical synthesizers or agricultural starters could mean the difference between a colony's survival and its collapse. This grants these freight corporations a form of soft power that rivals and may even surpass that of planetary governments. The new merchant class won't be captains haggling on a dockside. They will be faceless boards of directors and sophisticated algorithms making decisions that will echo across centuries and light years, building an economy where the most valuable currency isn't money, but reliable information and timely delivery. But these majestic star freighters cannot operate in a vacuum, quite literally. They require an entire ecosystem of support infrastructure, a network of ports and way stations that form the backbone of this new galactic economy. Picture the busiest seaport you can imagine, then translate that chaos and coordinated energy to the scale of the solar system. Envision a massive, rotating space station anchored at one of Jupiter's Lagrange points, a gravitational sweet spot where things can remain in stable orbit. This isn't a sterile scientific outpost, it's a gritty, thriving industrial hub. Massive freighters, having expended their fuel to escape the inner solar system's gravity well, dock here to refill their tanks with hydrogen skimmed from the gas giant's upper atmosphere. Smaller shuttlecraft buzz around them like worker bees, transferring standardized cargo containers from Earth and Mars orbit haulers onto the deep space vessels that will make the long journey outward. This is the interplanetary truck stop, the essential transfer point where local commerce becomes interstellar trade. The design of these facilities is a marvel of engineering in its own right. They would feature multiple docking arms capable of accommodating ships of vastly different sizes and configurations, from the sleek, fast couriers carrying high-priority data chips to the colossal, slow-moving bulk freighters hauling industrial equipment. The entire operation would be automated to an incredible degree. Robotic cranes and magnetic sleds would move cargo with a speed and precision impossible for human hands, orchestrated by a central traffic control AI that manages arrivals, departures, and transfers with nanosecond accuracy to prevent catastrophic collisions. For the rare human crews on long-duration routes, these way stations would offer a vital respite, a place to experience simulated gravity in rotating sections, breathe air that hasn't been recycled for months, and undergo medical check-ups before the next leg of their lonely journey. These hubs become the lonely oases in the desert of space, the only points of contact in a voyage defined by profound isolation. The most logical places to build this infrastructure are at Lagrange points and on resource-rich moons and asteroids. Lagrange points, those stable orbital parking spots created by the gravitational interplay between a planet and its sun, are perfect for construction. A station built at the Earth-Sun L1 point, for instance, is perpetually located between our planet and its star, making it an ideal starting point for ships heading out into the solar system. The real prize, however, lies further out. The moons of the gas giants like Europa, Callisto, and Titan are thought to hold vast oceans of water, making them the waterholes of the solar system where thirsty ships can refuel. Water isn't just for life support. It can be split into hydrogen and oxygen for conventional rocket fuel, or used as reaction mass in advanced propulsion systems. Building a refueling depot on a moon with abundant water ice is like building a gas station on top of an oil field, a strategically brilliant move that would make that location an economic powerhouse for centuries to come. Construction in the airless, zero-gravity environment of space demands entirely new techniques and materials. Why haul millions of tons of steel and aluminum from Earth's deep gravity well when you can mine it from nearby sources? This is where asteroids and mined lunar regolith come into play. Robotic miners would target metal-rich asteroids, processing the raw ore right there in space using solar furnaces. 3D printing on a monumental scale, using this sintered metal dust, could then fabricate the giant girders and hull plates needed for station construction. The European Space Agency has already demonstrated the feasibility of 3D printing using simulated lunar soil. This approach, known as in situ resource utilization, or ISRU, turns the construction problem on its head. Instead of being a handicap, the vacuum of space becomes an asset for certain manufacturing processes, and the abundance of raw materials in the asteroid belt becomes the quarry for building the infrastructure of the future. The funding and ownership of these critical choke points in the flow of interstellar commerce present a complex political and economic puzzle. The cost to build a single major orbital spaceport would dwarf the International Space Station's price tag, putting it beyond the reach of any single corporation or even most individual nations. This almost certainly leads to a model of international consortiums and public-private partnerships. Imagine a station funded by a coalition like the European Union, the United States, and Japan, but operated and maintained by a private logistics corporation like a future version of Maersk or SpaceX. They would generate revenue by charging docking fees, selling fuel, and offering maintenance services, effectively becoming the toll roads of the solar system. The potential for conflict is obvious. The entity that controls a critical refueling depot around Saturn effectively holds a veto power over all trade heading to and from that region of space. This necessitates the development of entirely new forms of interstellar law and trade agreements, drafted with the understanding that a delay or denial of service could mean the death of a colony light years away. Now let's peer into the cavernous holds of these vessels to understand what they're actually carrying. The contents define the mission, and in the realm of interstellar freight, cargo is king. Imagine a specialized container, a gleaming metallic cylinder etched with frost, humming with the low thrum of powerful cryogenic systems. Inside rests a treasure more valuable than any gem, a collection of cryogenically preserved plant samples and microbial mats, meticulously collected from the humid jungles of an Earth-like exoplanet light years away. This isn't a mere scientific curiosity. It's a vital shipment destined for a fledgling terraforming project on a barren moon, where these organisms will be tasked with the monumental job of breathing a new atmosphere into existence. This single container could determine the survival of an entire biosphere, a payload whose value is measured not in currency, but in the future of life itself. This example highlights the first major category of interstellar goods, perishables. This term extends far beyond food. It encompasses anything biological with a limited shelf life or specific environmental needs. Think of genetically tailored crops engineered for a colony's specific soil chemistry, live cultures for pharmaceutical production, or even the frozen genetic material of entire ecosystems, a library of life held in suspended animation. Transporting these materials demands ships that are essentially flying laboratories or arboretums, equipped with sophisticated life support systems, redundant power supplies, and immense shielding to protect delicate DNA from cosmic radiation. A single temperature fluctuation or power failure could ruin a cargo worth trillions and set a colony's development back by decades, making reliability the absolute paramount feature of these specialized biological arcs. In stark contrast to these fragile biological cargoes are the high-density goods, the raw minerals and refined materials that will form the literal building blocks of interstellar industry. Picture a freighter returning to our solar system, its hold packed with iridium and platinum group metals mined from the metallic core of a rogue asteroid in another star system. While common there, these elements are exceptionally rare on Earth's crust, yet they are absolutely critical for everything from advanced electronics and medical devices to the catalysts in hydrogen fuel cells. The economics are clear. The immense energy cost of an interstellar journey is only justified by an equally immense value per kilogram. You wouldn't ship iron ore, but you would ship a newly discovered superconductive mineral that operates at room temperature, a discovery that could revolutionize energy transmission across hundreds of worlds. These shipments will supply the high-tech manufacturing hubs of the inner solar system, creating a flow of incredibly valuable raw materials inward in exchange for the finished goods and data flowing outward. But perhaps the most surprising and initially dominant cargo will be the one that has no mass at all: digital data. As Dr. Mei Lin of the Interstellar Logistics Institute has famously argued, data transport will likely be the bedrock of the early interstellar economy. The information gathered by a multi-decade survey of a new planetary system, its gravitational mapping, atmospheric compositions, mineralogical surveys, and even petabytes of visual and sensor data is unimaginably precious. Delivering this data physically on a hardened diamond chip is more reliable than trying to beam it across light years where a signal could be degraded or lost. This data is the ultimate high-value, massless commodity. It's the blueprint that tells colonists where to land, what to mine, and what to avoid. It could also include cultural data, the entire collected art, literature, and history of one civilization sent to another, a time capsule traveling at relativistic speeds. The first ships might be more like library couriers than bulk haulers. This fundamental diversity in cargo types will inevitably lead to a parallel specialization in ship design. You wouldn't use the same truck to move gravel and surgical equipment, and the same principle applies across light years. We will see the emergence of distinct classes of interstellar freighters. Armored vault ships bristling with security systems and built like flying fortresses will be reserved for transporting antimatter fuel or processed exotic matter. Temperature-controlled biovessels with their intricate web of life support and monitoring systems will be the only choice for organic materials. Then there will be the data runners, smaller, faster vessels designed for velocity and reliability over brute cargo capacity, their precious solid-state drives protected by layers of redundancy. Each design presents a unique set of engineering challenges, driving innovation in materials science, propulsion efficiency, and autonomous operation. We can already see the faint outlines of this future in missions happening today. Take NASA OSIRIS-REx mission, which successfully landed samples from the asteroid Bennu back on Earth in 2023. This wasn't just a scientific achievement, it was a dry run for the core mechanics of interstellar freight. The mission involved precise rendezvous with a celestial object, careful collection and stowage of a precious material, a long-duration cruise phase, and finally, the delicate delivery of a capsule through atmospheric re-entry. Scale up the distance and timescale, and you have the basic prototype for a mineral freighter operation. It proves that we can already navigate the logistics of retrieving resources from one place in our solar system and delivering them to another. This entire new field of transport will demand a parallel development of something far less glamorous but equally critical: a comprehensive legal and regulatory framework. What protocols govern the transport of potentially hazardous biological materials? The last thing anyone wants is an extraterrestrial pathogen accidentally released upon arrival. How do you ensure a cargo that won't reach its destination for 50 years against risks that are literally unknowable? And who has jurisdiction over a contract dispute when the two parties involved are in different star systems and the journey itself has taken longer than the lifespan of the original signatories? These questions of interstellar law, safety, and insurance will require a global and eventually galactic consensus, creating a new branch of jurisprudence as vast as the space it seeks to govern. Navigating the unimaginable void between stars is arguably the most daunting hurdle for our future freighters. While propulsion gets the ship moving, it's the guidance system that ensures it doesn't become a permanent, silent monument drifting endlessly through the darkness. The challenges are unlike anything a sea captain or airline pilot has ever faced. There are no road signs in interstellar space, no GPS satellites to provide a fix, and no chance for a quick call to mission control when something goes wrong. The very laws of physics impose a cruel lag on communications. A message sent to a ship halfway to Proxima Centauri would take over 2 years to arrive, and the reply would take another 2 years to come back. By the time Earth even hears about a problem, the ship has been dealing with it or succumbing to it for half a decade. This forces a complete reimagining of shipboard operation, placing ultimate responsibility not on a human crew, but on a supremely advanced artificial intelligence. This AI captain would be a masterpiece of programming, a system capable of independent decision-making on a timescale that humans cannot perceive. Its primary mission is trajectory and hazard avoidance. Picture the ship entering a region akin to the Oort cloud, a vast shell of icy debris surrounding our solar system. Here, it encounters a dense meteor shower not on any chart. The AI, processing terabytes of data from its forward-looking LiDAR and radar arrays in milliseconds, must calculate a new course instantaneously. It cannot wait for human input. By the time a request for guidance reached Earth and a response returned, the ship would have long since passed through the danger zone or collided with it. The AI executes a complex series of micro-burns from its attitude thrusters, the vessel shifting its massive bulk with gentle precision to weave through the field of ice and rock, its sensitive hull layers and cargo safeguarded from catastrophic impact. This isn't a moment of panic, it's a routine calculation for the machine mind at the helm. To make these critical decisions, the AI relies on the most accurate maps possible. But how do you chart a course through territory that is, by definition, largely uncharted? The solution lies in creating a dynamic, ever-updating network of cosmic beacons. While we can't use fixed satellites, we can use the universe's own natural lighthouses, pulsars. These rapidly spinning neutron stars emit beams of radiation with a regularity that rivals atomic clocks. Each pulsar has a unique signature, a specific rhythm that allows it to be identified. By triangulating its position relative to a catalog of known pulsars, a ship can determine its location in the galaxy with remarkable accuracy, essentially creating a galactic GPS. This data would be supplemented by a fleet of automated scout probes, dispatched years or even decades ahead of the main trade routes. These pioneers would travel to key navigational points, taking detailed readings of gravitational fields, mapping dust clouds, and identifying potential hazards, then broadcasting this invaluable data back for the freighters that follow, turning the unknown into the familiar one data point at a time. The communication problem is perhaps even more frustrating than navigation. The speed of light, while incredibly fast, is agonizingly slow for interstellar commerce. This is where theoretical physics offers a tantalizing, though still unproven, solution: quantum entanglement. In theory, if two particles are entangled, a change to one will instantly affect its partner, regardless of the distance separating them. If this principle could be harnessed, it could allow for real-time communication across light years, breaking the light-speed barrier. Imagine the ship's AI being able to send an instantaneous status report to its home office, or receiving immediate instructions if a complex ethical decision about jettisoning cargo arises. While the practical challenges of creating and maintaining stable, long-distance entangled pairs for data to transmission are monumental and may never be overcome, the mere possibility drives intense research, as it would utterly revolutionize the safety and efficiency of galactic trade. In the more likely near-term scenario, where light-speed lag is an immutable fact of life, redundancy becomes the single most important design philosophy. Every critical system on the freighter, from navigation and propulsion to life support and communication, would be triplicated or even quadruplicated. The ship's brain wouldn't be one AI, but three, operating in a constant consensus. They would vote on major course corrections, and if one unit began to malfunction or provide erroneous data, the other two could outvote it and isolate it from the network. This extends to physical components as well. The failure of a single valve or circuit board cannot be allowed to doom a multi-trillion-dollar mission. The ship would carry extensive spares and host onboard fabricators capable of manufacturing replacement parts, all managed by those ever-vigilant repair drones. The entire vessel is designed for a simple, brutal reality. There is no cavalry coming. It must be its own rescue party. This profound isolation also presents an immense psychological challenge for any human crew members on these decade-long voyages. While early freighters may be entirely autonomous, later models might include small caretaker crews for overseeing complex cargo or making nuanced judgments beyond an AI's purview. These individuals would face a test of mental fortitude unlike any other in human experience. They would be separated from everyone they have ever known by an unbridgeable gulf of time and space, watching as messages from home arrive years out of sequence, describing events that are ancient history. To cope, crews would likely undergo rigorous psychological screening and training, and ships would be equipped with virtual reality environments, extensive libraries, and communication systems designed to create a semblance of connection, even if it's with a recording of a loved one who has aged years since the message was sent. Theirs would be a life of ultimate professionalism, where focus on the mission and the safety of the cargo becomes the anchor that holds their reality together. Protocols for emergencies would be drilled into the very core of the ship's operational doctrine. A containment breach in a biocargo hold, a sudden drop in power from the main reactor, a micrometeorite puncture. Each scenario has a pre-programmed response, a digital playbook written by the best engineers and strategists decades before the ship ever left port. The AI would execute initial containment procedures while alerting the human crew, who would then work through verified checklists. The concept of mission control shifts from a room on Earth to a decentralized network of the ship's own systems and the collective expertise of its crew. Their decisions in those critical moments would be final, with the full understanding that those on Earth will only learn of their success or failure years after the outcome has been decided. This incredible burden of responsibility makes the crew of an interstellar freighter the most self-reliant explorers in history, their success resting on their ability to be the masters of their own destiny in the infinite black. Imagine a corporation based on Mars filing a claim against a settlement in the Proxima Centauri system over exclusive rights to a vast lithium deposit discovered on a rocky moon. The Martian company argues their survey probe identified it first. The Procyon settlers claim they were the first to physically land and plant a flag. Who decides? There is no planetary government with jurisdiction, and a message explaining the dispute to Earth would take over 4 years to arrive, let alone a verdict. This is the kind of convoluted scenario that demands an entirely new branch of jurisprudence, interstellar trade law. The current framework governing space, primarily the 1967 Outer Space Treaty, is a noble but outdated document focused on preventing weapons of mass destruction in space and declaring that no nation can claim sovereignty over a celestial body. It was written for an era of flags and footprints, not for the complex trillion-dollar logistics of galactic commerce. It says nothing about who owns the minerals and asteroid miner extracts, how to ensure a cargo of prototype nanobots against an unforeseen supernova, or what protocols must be followed to prevent a spacecraft from accidentally contaminating a pristine alien biosphere with Earth microbes. This legal vacuum presents one of the single greatest risks to the development of an interstellar economy. Large-scale investment requires predictability and the rule of law. No bank will finance the construction of a freighter, and no insurance company will underwrite its cargo if there are no clear rules governing liability in case of an accident or clear legal recourse in case of a dispute. The solution, as space law expert Dr. Rajiv Mehta advocates, will likely be the creation of a new international, or rather inter-system, body, a galactic economic authority. This wouldn't be a world government, but a neutral regulatory and arbitration organization, similar to the World Trade Organization or the International Seabed Authority here on Earth. Its power would derive from treaties signed by participating solar nations and colonies, who agree to abide by its rulings in matters of trade, resource rights, and environmental safety. Its first and most crucial task would be to establish a clear code defining property rights. The current finders-keepers model is a recipe for conflict. Instead, a system of claims, likely based on a combination of first discovery, first exploitation, and sustainable development, would need to be codified and registered in a central ledger accessible to all. The parallels to maritime law are striking and provide a valuable blueprint. For centuries, admiralty law has governed commerce on the high seas, territories that belong to no single nation. It establishes standard rules for shipping contracts, liability for lost or damaged cargo, and the right of innocent passage. An interstellar legal framework would need its own version of these universal standards. What is the liability if a freighter's navigation error causes it to collide with a scientific outpost? How is a cargo of genetically engineered organisms classified and insured? The concept of marine insurance, which spread risk among many underwriters for dangerous voyages, would be directly adapted to create complex new financial instruments for interstellar missions, policies that account for relativistic time dilation and cosmic scale acts of God. Perhaps the most critical and ethically charged area of regulation will be planetary protection. The Outer Space Treaty contains vague language about avoiding harmful contamination of celestial bodies, but this must be transformed into strict, enforceable protocols. The consequences of negligence are existential. A freighter operating with inadequate sterilization procedures could inadvertently transport an invasive Earth microbe to a planet like Proxima Centauri b, wiping out native life forms before they are even discovered, or conversely, bring an unknown alien pathogen back into our solar system. The GEA would need the authority to mandate decontamination procedures, quarantine periods, and rigorous cargo inspection at designated ports of entry, treating each starship not just as a vessel of commerce, but as a potential vector of ecological catastrophe. This then leads to the complex question of enforcement. What penalties apply to a corporation that violates these regulations, or to the much darker threat of interstellar piracy, a rogue vessel hijacking a freighter for its valuable cargo in the deep void between stars? There is no interstellar police force. Enforcement would initially have to be economic and collective. A company found guilty of violating trade laws or environmental protocols could be blacklisted by the GEA, its ships denied docking privileges at all major ports, and its financial assets frozen by member states. This collective sanction makes following the rules far more profitable than breaking them. For more serious crimes like piracy, the only solution may be a system of licensed private security, akin to the armed guards on modern cargo ships sailing through pirate-infested waters, authorized to use force to protect their vessel and its priceless cargo. The law in deep space will ultimately be upheld not by a centralized authority, but by a system of mutually assured commercial interest, where cooperation and adherence to a common rule set is the only viable path to prosperity for all. The sheer complexity and timescales involved make the reliance on advanced artificial intelligence not just a matter of efficiency, but an absolute prerequisite for survival. These are not ships that can be piloted by human hands. They are ecosystems of automated systems managed by a central, hyper-intelligent AI captain. Think of it as the world's most advanced autopilot, but one that must operate with complete autonomy for decades, making life or death decisions without any possibility of human consultation. Its primary role is to serve as the ship's omnipresent mind, constantly monitoring a flood of data from thousands of sensors, from the subtle vibrations in the fusion reactor's magnetic coils to the microscopic erosion on the leading edge of the hull from interstellar dust. It runs perpetual simulations, predicting potential system failures weeks or months before they occur, and dispatching its fleet of robotic repair drones to perform preemptive maintenance, effectively giving the ship an immune system that fights problems before they even manifest. This AI's most critical function is navigating a constantly shifting sea of hazards. It processes real-time cosmic weather reports, detecting the precursor radiation of a distant coronal mass ejection from a star not on its original charts, and calculating a new course to avoid the storm of high-energy particles. It uses its powerful LiDAR arrays to map fields of micrometeoroids too small to see from Earth, plotting a safe path through the celestial minefield. The system's machine learning algorithms are trained on petabytes of data from previous voyages, allowing it to recognize patterns and anomalies that would be invisible to a human operator. It might notice a faint gravitational perturbation suggesting a previously unknown dwarf planet or a rogue black hole drifting through its planned route, prompting a course correction that saves the mission. This isn't programming, it's a form of digital instinct honed by experience it gathers across light years. The automation extends deep into the ship's core functions, particularly cargo management. In the zero-gravity environment, human loading and unloading is impractical and dangerous. Instead, the hold is a dynamic, self-organizing warehouse. As each standardized container is loaded by automated dockside systems, it is scanned and its contents logged into the AI's manifest. Robotic sleds and magnetic cranes, guided by intricate internal positioning systems, slot each container into a precise location, balancing the ship's mass for optimal fuel efficiency. The AI knows the destination of every item and can, entirely on its own, reorganize the cargo mid-flight to prepare for the most efficient unloading sequence upon arrival. It constantly monitors the environmental conditions within specialized holds, adjusting temperature, humidity, and radiation shielding to ensure a payload of delicate biological samples or unstable chemical compounds remains perfectly preserved for the entire decades-long journey. When it comes to the economics of the mission, the AI's role evolves from a pilot to a corporate executive. Equipped with sophisticated economic modeling software and real-time, though years delayed, market data feeds, it is authorized to make autonomous trading decisions. Imagine the ship arriving in the Proxima Centauri system after its 40-year journey. The AI immediately establishes a communication link and downloads 50 years of economic data from the colony, analyzing shifts in supply, demand, and local currency valuation. It discovers that while its primary cargo of industrial replicators is still valuable, a secondary cargo of specific medical isotopes is now astronomically more sought after due to a recent pandemic. The AI can then negotiate the sale, using pre-programmed negotiation parameters to secure the best possible price for its owners back in our solar system, finalizing transactions that won't be ratified by humans for another 8 years. It acts as a remote, autonomous agent of its corporate masters, maximizing return on an investment that spans generations. This level of autonomy inevitably raises profound ethical and safety questions. The core dilemma is known as the captaincy problem. At what point does the AI's authority override that of any human crew on board? Should it have the power to jettison cargo to save the ship? Could it be authorized to sacrifice a damaged section of the vessel, even if it contained human occupants, to ensure the survival of the mission and its critical cargo? These are not hypotheticals. They are scenarios that must be hard-coded into its ethical decision-making matrices before launch. To prevent malfunctions or the nightmarish scenario of a rogue AI, these systems are built not as a single intelligence, but as a layered consensus of independent neural networks. 3 separate AI minds would constantly cross-check each other's calculations. If one begins to deviate or develop an error, the other 2 can outvote it and isolate it from the ship's controls, a digital failsafe that ensures no single point of failure can doom the entire mission. The development of these systems is already underway, seen in the rapid evolution of autonomy on Earth. Tesla's self-driving technology is a rudimentary precursor, a system that must perceive its environment, predict the actions of other agents, and make safe navigation decisions in real time. Scale that up to the complexity of interstellar space, and you begin to understand the challenge. The role for humans in this automated future shifts from operators to overseers and high-level decision-makers. People will be needed to set the strategic goals, to program the ethical constraints, and to handle the supremely complex, non-linear problems that fall outside the AI's training data. They become the curators of the mission's purpose, while the machine handles the infinitely complex details of its execution. This partnership between human ingenuity and machine precision is the only formula that can unlock the vast economic potential of the galaxy, turning the silent, empty void into a highway for commerce. The sheer energy required to push a million-ton vessel across light years demands a radical rethinking of refueling, transforming the act from a simple pit stop into a breathtaking feat of cosmic engineering. Forget pulling into a station. Imagine the ship itself becoming a predator, hunting for its next meal in the atmosphere of a gas giant. The Merchant's Hope approaches Jupiter, its course carefully calculated to skim the upper layers of the colossal planet's swirling hydrogen-helium atmosphere. From its belly, it deploys a massive, funnel-shaped magnetic scoop, an invisible net that gathers and compresses the thin gas. This isn't just a fuel stop, it's a demonstration of the core principle that will enable a galactic economy: in situ resource utilization, or ISRU, the ability to live off the land, using the resources found in space to enable further exploration. By harvesting fuel directly from the destinations it visits, the freighter breaks its dependence on Earth, becoming a truly self-sufficient entity capable of voyages that last for centuries. The primary fuel for this first generation of ships will almost certainly be for nuclear fusion, and the recipe is deceptively simple yet incredibly difficult to source. The engine craves two isotopes, deuterium and helium-3. Deuterium, a heavy form of hydrogen, is relatively abundant. It can be extracted from water, and thus from the icy moons of the outer solar system or from the hydrogen scooped from gas giants. The real prize, the component that makes fusion so potent and efficient, is helium-3. This rare, non-radioactive isotope is incredibly scarce on Earth, but it is thought to be implanted by the solar wind in vast quantities within the powdery regolith of the Moon. This is why lunar mining will be one of the first major off-world industries. Enormous automated combines could strip mine the lunar surface, heating the soil to release trapped helium-3 for collection, turning our Moon into the Persian Gulf of the early solar system, a central fueling hub for the fledgling starfaring fleet. For those looking beyond fusion, the ultimate energy source beckons: antimatter. The complete matter-antimatter annihilation offers an energy density millions of times greater than chemical fuels or even fusion. The problem is production and storage. Creating even a single gram of antimatter requires staggering amounts of energy, likely generated by massive orbital solar farms or more efficient fusion reactors dedicated solely to this purpose. Some theories suggest harvesting naturally occurring antimatter from the magnetic fields of planets like Jupiter, which trap tiny amounts created by cosmic ray interactions. Once produced, storing it is a nightmare of physics. It must be held in a perfect vacuum within powerful electromagnetic bottles called penning traps, where a single flaw would result in a catastrophic explosion. The payoff, however, is a fuel so potent that a freighter could make a round trip to a nearby star within a human lifetime, utterly transforming the economic model from one-way investments into a viable, repeating trade loop. This necessity gives rise to a new kind of strategic asset, the Deep Space Fuel Depot. As leading propulsion expert Dr. Ilara Vance from the Institute for Advanced Concepts explains, the locations of these depots will not be arbitrary. They will be dictated by celestial mechanics and resource availability. The Lagrange points around gas giants like Jupiter and Saturn will become the truck stops of the solar system. Here, at these gravitational sweet spots, processing stations will operate continuously, siphoning hydrogen from the gas giants or receiving shipments of helium-3 from the Moon. They will purify and store these volatile fuels, ready to service the freighters passing through on their way to the outer solar system and beyond. Control of such a depot won't just be a business, it will be a form of immense strategic power, a choke point that can enable or stifle the flow of interstellar commerce. We are already prototyping the fundamental techniques for this future here and now. NASA's ambitious plans for human missions to Mars are deeply reliant on ISRU technology. The agency is developing systems to extract water from Martian ice deposits and then use electrolysis to split it into liquid oxygen and hydrogen for rocket propellant. The goal is to enable astronauts to literally manufacture their return fuel on the surface of the red planet, proving that we can break the chain of total dependence on Earth. This is the crucial first step, the small-scale proof of concept that will eventually be scaled up to the level of scooping atmospheres of gas giants. Every robotic mission that analyzes soil composition or tests a resource extraction technology is laying another brick on the road to the stars. This expansion inevitably raises complex questions about our environmental responsibility beyond Earth. The extraction of helium-3 from the lunar surface, for instance, would require processing enormous quantities of regolith, permanently altering the landscape of our moon. What are the ethical implications of strip mining a celestial body that holds cultural and scientific significance for all of humanity? The principle of planetary protection must evolve to include not just biological contamination, but also industrial and aesthetic preservation. Sustainable practices will need to be developed, perhaps setting aside wilderness areas on the moon or other worlds as protected parks, ensuring that our economic expansion into the solar system does not come at the cost of irrevocably destroying pristine environments before we even fully understand them. Ultimately, the entire economic viability of interstellar freight hinges on solving the fuel equation. The frequency and cost of freighter runs are directly tied to the availability and price of propellant. A reliable, sustainably sourced fuel supply chain within our own solar system drastically reduces the cost of launching an interstellar mission, as the ship doesn't have to carry all the fuel for its entire journey from the start. It can top up at depots, making the economics more akin to a modern container ship refueling at major ports rather than a solitary rocket launching on a one-way trip. This logistics network is the unseen backbone of the galactic economy, the mundane yet utterly critical infrastructure that makes the romantic vision of star sails and warp drives a practical, functioning reality. The companies that master this supply chain will not just be fueling ships, they will be fueling the future of civilization itself. While the image of a completely automated starship is compelling, the reality of the first interstellar freight missions will almost certainly include a human element. Artificial intelligence may manage the ship's systems, but humans will be indispensable for their adaptability, problem-solving skills, and nuanced judgment. Picture a crew of 20, not hundreds, embarking on a journey that will last decades. They are not just employees, they are the founding members of a micro-society adrift in the void, a self-contained culture that must function flawlessly under unimaginable pressure and isolation. The selection process for these individuals will be one of the most rigorous in human history, far surpassing that of astronauts or submariners. It won't be about finding the best pilot or the smartest engineer, but about identifying the most resilient, balanced, and cooperative individuals who can form a functional family unit cut off from the rest of humanity. The ideal crew profile will likely be a hybrid of diverse backgrounds. You might have a few ex-military personnel, valued not for combat skills but for their ingrained discipline and experience operating complex machinery in high-stress, long-duration environments like nuclear submarines. Alongside them would be career scientists and engineers with deep cross-disciplinary training, a mechanical engineer who also understands botany to maintain the life support systems, or a data systems specialist with medical training to serve as the crew's doctor. The key is redundancy in skills and a temperament that thrives in a closed environment. Psychologists will be looking for individuals with high emotional intelligence, a low propensity for conflict, and a powerful intrinsic motivation that goes beyond financial reward. These are people who genuinely believe in the mission's importance, because that belief will be their anchor when Earth is nothing but a faint blue dot in the rear-view screen, and the loneliness of the voyage becomes palpable. Life aboard the freighter will be a study in controlled, sustainable existence. The ship itself is a closed-loop ecosystem, constantly recycling air and water. Hydroponic farms lit by full-spectrum LEDs will provide fresh food and play a crucial psychological role, offering a tangible connection to life and growth in an otherwise sterile metal environment. These gardens will be a place of respite and duty, a reminder of the world they left behind and the one they are helping to build. Recreational facilities, while limited by space, will be critical for mental health. Virtual reality systems could offer immersive escapes to familiar Earth environments or fantastical worlds, while extensive digital libraries, film archives, and interactive games will provide intellectual stimulation and a crucial distraction from the monotony of the long cruise phases between course corrections. The social dynamics of this isolated group will be the subject of intense study. We can look to existing analogues for clues, the crews of Antarctic research stations like McMurdo, or the scientists who winter over at the South Pole, isolated for months in the darkness. These communities develop their own unique traditions, slang, and social hierarchies. Conflict resolution protocols will be a core part of the ship's operational doctrine, with regular mediated check-ins and a clear, agreed-upon process for addressing grievances before they fester. The ship's captain won't just be a manager of systems, but a leader of people, a diplomat, a counselor, and sometimes a judge. Their most important skill will be maintaining crew cohesion and morale over a timescale that dwarfs any military deployment or space mission in history. One of the most profound challenges will be the crew's connection to home. Communication with Earth will be defined by a crushing time lag. A message sent from the ship will take years to reach its destination, and a reply will take years to return. This isn't a conversation, it's sending a message in a bottle and waiting a decade for a response. This forces a complete rethinking of family and social ties. Will crew members be allowed to have partners and children on Earth, knowing they will age decades during the voyage? Some missions might be structured as generational ships from the start, with crews comprising entire families. Others might operate on a celibacy model, with crew members accepting that they are sacrificing a terrestrial family life for the mission. The communication systems will therefore focus on asynchronous updates, sending long video diaries and receiving massive data packets of news, cultural updates, and personal messages from loved ones, all of which will be consumed as historical records from a past that is constantly receding. This strange relationship with time and distance will be the single greatest psychological hurdle, creating a crew that is physically together in the present but mentally connected to an Earth that exists only in their shared memory. This expansion into the galaxy forces us to confront a fundamental question that echoes from our own history. Do we have the right to take whatever we find, or do we have a responsibility to preserve what we encounter? The vision of mining a pristine metallic asteroid, untouched since the dawn of the solar system, presents a classic conflict between unchecked economic ambition and a newfound interstellar environmental ethic. On one hand, that asteroid represents a virtually limitless supply of iron, nickel, and precious platinum group metals, a bounty that could build orbital cities and fuel economic growth for centuries. On the other, it is a celestial body with its own unique geological history, a natural relic that could hold scientific secrets about the formation of our solar system, and its alteration would be permanent and absolute. This is not a hypothetical debate. It is the central ethical dilemma that will define the soul of our galactic economy. The risks extend far beyond mere scenic preservation. One of the most serious concerns is the threat of biological contamination, a problem that operates in two terrifyingly opposite directions. Forward contamination occurs when a freighter, its hull or cargo imperfectly sterilized, inadvertently transports Earth-based microbes to a new world. A single hardy bacterium surviving the journey in a dormant state could be released upon arrival and wreak havoc on a fragile, nascent alien ecosystem, potentially outcompeting native organisms or even consuming them before we ever have a chance to study them. The reverse scenario, back contamination, is equally alarming. A returning freighter could carry an unknown extraterrestrial microorganism back to Earth, a pathogen for which we have no natural immunity, potentially triggering a pandemic that could make historical plagues look mild by comparison. These are not the plots of science fiction movies. They are legitimate, catastrophic risks that must be engineered out of existence through rigorous decontamination protocols and strict quarantine procedures for all vessels moving between biospheres. To navigate this ethical minefield, leading thinkers like astrophysicist Dr. Samara Kouachi proposed the establishment of a neutral, interplanetary body akin to a galactic environmental agency. This wouldn't be a world government, but a regulatory organization with the authority to set and enforce standards across all human activity in space. Its mandate would be profound: to designate protected wilderness areas on moons and asteroids, to establish sustainable harvesting quotas for resources based on scientific assessment rather than corporate greed, and to certify that all spacecraft meet the highest possible standards of planetary protection. It would act as a referee in disputes, using the collective economic power of its member states to sanction entities that violate these crucial rules, perhaps by denying them docking rights at major ports or freezing their financial assets. Its core principle would be that the resources of the galaxy are a common heritage, not a free-for-all to be plundered by whoever arrives first with the biggest drill. We already possess a sobering case study for what happens in the absence of such oversight: our own planet's history of resource exploitation. The near extinction of the American bison for their hides, the deforestation of entire regions for timber, and the tragic overfishing of cod stocks in the North Atlantic all serve as powerful warnings. In each instance, short-term economic gain was prioritized over long-term sustainability, leading to ecological collapse and the loss of something irreplaceable. The lessons are clear. The tragedy of the commons, where a shared resource is depleted by individuals acting in their own self-interest, is a pattern we must consciously break as we move into the solar system. The asteroid belts and icy moons of our galaxy must not become the new fishing grounds, mined to exhaustion until there is nothing left for future generations. This leads to the most profound ethical question of all. What do we do if we find life? Imagine a freighter's advanced scout probe sending back data from a moon like Europa, confirming not just the presence of a subsurface ocean, but the existence of complex multicellular organisms within it. This discovery would immediately turn that moon from a potential resource to be exploited into a sanctuary to be protected. The economic implications would be staggering. A planned mining operation for the moon's subsurface minerals would have to be immediately halted. A fueling depot designed to process its water ice would become unthinkable. The entire trade route might need to be rerouted to maintain a safe distance and prevent any possible contamination from a passing ship. In this scenario, the profit and loss spreadsheet must be discarded in favor of a higher principle: the preservation of life itself, especially life that arose independently of our own. This would be the ultimate test of our species' maturity: proving that we can prioritize discovery and reverence over conquest and consumption. Establishing a framework for these decisions requires us to develop a new branch of ethics itself. How do we assign value to an alien environment? Is a bacterial mat on Mars less worthy of protection than a complex ecosystem on a moon of Saturn? Does the potential to support human life in the future give a planet more rights than one that cannot? These are questions without easy answers, and they will be debated by philosophers, scientists, and lawmakers for decades. Practical solutions will likely involve a tiered system of planetary protection, with the most stringent regulations applied to worlds with the highest potential for native life, and more flexible rules for barren, resource-rich asteroids. The development of non-invasive mining techniques, such as using automated drones that leave the majority of a celestial body intact, will be crucial. The goal is not to halt progress, but to guide it responsibly, ensuring that our expansion into the galaxy is marked by wisdom and foresight, rather than remembered as a new wave of colonial extraction. Our legacy among the stars will be judged not by the wealth we extract, but by the wonders we choose to leave untouched. Before we can even dream of sending cargo between stars, we must first master the highways in our own celestial backyard. This critical proving ground is already taking shape, not in the silent void between suns, but in the bustling, resource-rich space between Earth and the asteroid belt. The first true milestone on the path to a galactic economy is the establishment of a thriving inner solar system trade network, a complex web of supply chains that will turn the worlds and rocks around our sun into the workshop for humanity's future. This isn't a far-off speculation. It's the active, unfolding business plan of a new generation of space enterprises, and it will serve as the indispensable training wheels for the vastly more complex endeavor of interstellar shipping. Picture the scene: a sleek, automated freighter, its hull scarred by micrometeoroid impacts, maneuvers with gentle puffs of cold gas thrusters to dock with a spinning orbital station above Mars. Its hold is filled with pristine water ice, mined from a carbonaceous asteroid in the belt. This water won't be for drinking. It will be split into hydrogen and oxygen to fuel the next wave of ships heading out from the red planet, and it will be used to support the expanding greenhouse domes of the fledgling colony below. On its return trip to Earth, the same ship will be loaded with specialized metal alloys, manufactured in the low-gravity factories of Mars orbit, where unique and perfect products can be created under conditions impossible to replicate on Earth. This is the inner system economy in action, a constant, cyclical exchange of raw materials, manufactured goods, and life-sustaining volatiles that turns dead rocks into valuable real estate. The engine of this new economy is asteroid mining, and the targets are as valuable as they are numerous. Companies that once seemed like science fiction, such as Planetary Resources and Astroforge, are developing the core technologies to make this a reality. They're not just after precious metals like platinum and gold, though those will provide the initial economic incentive. The real jackpot is water. Water is the oil of space exploration. It's heavy, expensive to launch from Earth's deep gravity well, and absolutely essential not just for human survival, but as a radiation shield and, when split into its components, as rocket fuel. Finding and extracting water from water-rich, C-type asteroids effectively creates a network of celestial gas stations, breaking our total dependence on Earth and making the rest of the solar system accessible. The first company to successfully mine and sell water in orbit will fundamentally change the economics of spaceflight, slashing the cost of deep space missions by orders of magnitude. This activity is being actively encouraged and funded by governments, turning what was once purely national exploration into a public-private partnership. NASA Artemis program is a perfect example. Its goal isn't just to return astronauts to the moon, it's to establish a sustainable lunar economy. The Lunar Gateway Station will act as an outpost and potential transfer point for resources. The plan includes prospecting for and extracting water ice from permanently shadowed lunar craters, with the intent of creating a functioning market for lunar propellant by the 2030s. This government-led infrastructure provides the initial anchor customers and basic framework that private companies can then build upon, creating a stable economic environment for investment and innovation. It's a modern-day equivalent of the government building highways and ports, which in turn enables countless private businesses to flourish. The ripple effects of this off-world resource harvesting will cascade back to Earth in profound and sometimes unexpected ways. The abundance of certain rare metals from asteroids could suddenly make them commonplace, revolutionizing industries back on our home planet. Imagine platinum becoming so cheap and plentiful that it becomes the standard catalyst in every hydrogen fuel cell vehicle, accelerating the transition away from fossil fuels. Or new super-strong alloys developed in zero-gravity smelters, enabling the construction of space elevators or next-generation aircraft. The economic model shifts from one of scarcity on a single planet to one of abundance drawn from millions of sources throughout the solar system. This doesn't devalue Earth's economy. It supercharges it by providing access to previously unimaginable resources and enabling new technologies. Mastering this inner system trade is a non-negotiable prerequisite for any interstellar ambition. Every challenge we solve closer to home is a lesson directly applicable to the greater void. The logistics software that manages the launch windows, orbital rendezvous, and cargo transfers between Earth, Mars, and the Belt is a prototype for the infinitely more complex software that will need to guide a ship for decades without any input. The autonomous navigation systems that allow a mining drone to land on a tumbling asteroid are a test run for the AI that will have to navigate a freighter through the Oort cloud. The legal frameworks developed to govern mineral rights on an asteroid will become the foundation for the interstellar trade laws that will one day manage commerce between star systems. This phase is where we work out the kinks, make the mistakes, and develop the confidence needed to take that next, much larger leap. The expertise gained isn't just technical, it's also human. The first crews operating these interplanetary freighters will be pioneers in their own right, learning to live and work in space for years at a time, managing the psychological strain of isolation while maintaining peak professional performance. They will develop the protocols for long-duration missions, the maintenance schedules for systems that cannot be easily replaced, and the cultural norms of a society that lives off-planet. These individuals and the organizations they work for will become the core around which the first true interstellar shipping lines are built. Their experience will be the most valuable cargo they carry, a living library of best practices for surviving and thriving in the cosmic ocean. The road to the stars isn't built in a single launch. It's paved with every successful delivery between Mars and Earth, every ton of water ice extracted from an asteroid, and every new law written to keep the peace in this new frontier. This bustling, profitable, and practical inner solar system economy is the essential nursery where our galactic future is being born. The moment that first dedicated freighter, perhaps named the Pathfinder 1, ignites its engines and commits to a trajectory out of our solar system toward Alpha Centauri, will mark a turning point for our species as profound as the first wooden ships setting sail across an unknown ocean. Its cargo might seem modest, a suite of advanced telescopes and atmospheric spectrometers, but its purpose is monumental: to conduct the first dedicated commercial survey of potentially habitable worlds, scanning for biosignatures and mineralogical data that will dictate the flow of trillions in future investment. This leap from interplanetary to interstellar trade is not merely an extension of distance. It is a fundamental shift in the nature of commerce, planning, and human ambition, all centered on overcoming the most formidable barrier of all, the void itself. Choosing these initial trade routes is a complex calculation that blends cold economics with the dream of expansion. The first targets will undoubtedly be our closest stellar neighbors, with the Alpha Centauri system, a triple-star system just over 4 light-years away, standing as the prime candidate. Proxima Centauri, the smallest of the three, is already known to host a rocky planet, Proxima Centauri b, within its habitable zone, making it an irresistible first destination for both scientific and economic scrutiny. But proximity isn't the only factor. Barnard's star, a single red dwarf, is the next closest system and could be a valuable second target, while more distant but promising systems like Tau Ceti, known for its sun-like star and potential planets, might round out the first wave of interstellar commerce. The selection process will involve a painstaking analysis of decades of astronomical data, weighing a system's resource potential, the presence of asteroid belts or gas giants for fueling against its potential for hosting life, as a habitable world represents the ultimate long-term customer and colony. The blueprint for this audacious leap is already being drafted by projects that sound like they're pulled from science fiction. Breakthrough Starshot, for instance, is a serious research initiative aiming to use powerful ground-based lasers to propel a fleet of tiny, gram-weight nanocraft attached to light sails to Alpha Centauri at 20% the speed of light. While the Starshot craft themselves are just data-gathering probes, the technologies they are pioneering, super lightweight materials, laser propulsion, and miniaturized systems, are directly informing the design of future freighters. The lessons learned in building a communication system that can send a signal across 4 light-years will be invaluable. The challenges of shielding a craft from interstellar dust impacts at relativistic speeds will provide critical data for designing the armored hulls of future cargo vessels. Starshot is the proof of concept, the tiny scout that runs ahead of the main caravan to survey the trail. For any crewed missions which may be necessary for complex on-site analysis or repairs, the human element introduces a staggering set of biological and logistical challenges. The concept of generation ships, vast arcs where multiple generations are born, live, and die during the centuries-long voyage, presents profound ethical questions about consent and purpose for those born into the journey. A more plausible near-term solution is sleeper ships, where crews enter a state of suspended animation or biological stasis, effectively pausing their metabolism for the majority of the decades-long transit. This technology, while still in its infancy with research focused on medical applications for trauma patients, would allow a specialized crew to be on ice for the journey, awakened only for critical decision-making points or upon arrival to perform their duties with fresh minds and bodies. This turns a multi-generational epic into a single-generation professional assignment. The economics of these voyages will initially favor a one-way model that seems counterintuitive to our terrestrial experience. A freighter might be launched from Earth with a cargo of sophisticated, lightweight, high-value goods, advanced medical nanobots, genetic libraries, or master copies of cultural and scientific databases. It would spend decades traveling to its destination, where it would be met by local craft from the fledgling colony. After offloading its precious cargo, the freighter itself, now empty, would become a permanent asset in that star system. Its reactor could provide power, its hull could be repurposed into living quarters or a research facility, and its advanced onboard AI and fabrication systems would become a cornerstone of the colony's industrial base. The return on investment isn't the ship coming back, but the data it sends back. The colony would transmit payment in the form of exoplanetary survey data, confirmed resource maps, and cultural discoveries, information that is massless but immeasurably valuable to the sending civilization, creating a completely new interstellar data market. This bizarre economic model raises the critical question: what incentive could possibly drive a private company or consortium to invest billions in a project that won't see a return for half a century or more? The answer lies in a combination of extreme long-term vision and new financial instruments. The investors will not be individuals expecting a quick profit, but legacy-focused entities like sovereign wealth funds, multi-generational family offices, and mega-corporations with century-long business plans. They will treat it as infrastructure investment on a galactic scale. The financing will likely involve the creation of novel, century bonds and interstellar futures contracts, where the value is based on the projected worth of the data and resources at the time of arrival. Insurance would be a consortium model, spreading the immense risk of a total loss across many parties. The driving force, beyond mere profit, will be the guarantee of strategic advantage. The first entity to establish a reliable data pipeline from a new star system will hold an informational monopoly that could dictate the future of human expansion, a prize worth almost any price. Picture the shimmering ring of a space station in orbit around Proxima Centauri b, its docks bristling with the spindly forms of freighters from a dozen different solar systems. This isn't just a port, it's a galactic crossroads, the Rotterdam or Singapore of the interstellar age, where goods, data, and cultures from across the light years converge. The establishment of such hubs isn't a matter of if, but where, and their locations will be dictated by the same ancient principles that gave rise to terrestrial trading posts: strategic position and resource abundance. Proxima Centauri is the obvious first candidate, our closest stellar neighbor, offering a rocky world in the habitable zone. Its prime value lies not just in its real estate, but in its location as the natural gateway for ships pushing further out into the galactic arm, making it an indispensable waypoint for refueling and resupply before the next long jump into the unknown. Yet proximity is just one factor. A system like TRAPPIST-1, with its 7 rocky worlds, 3 sitting snugly in the habitable zone, presents a different kind of allure. As astrophysicist Dr. Liam Chen notes, a single system with multiple potentially life-bearing worlds is an unprecedented economic opportunity. Instead of one port serving one colony, you could have a network of specialized hubs within the same gravitational sphere. One station focused on biological exports from a world rich in unique flora, another serving as a mineral processing center for a resource-rich barren moon, and a third acting as the central administrative and financial capital. The sheer density of opportunities within such a compact system would create a microcosm of the galactic economy, a vibrant, interconnected web of trade that could make TRAPPIST-1 a dominant economic powerhouse. Binary star systems offer another fascinating possibility. The complex gravitational interactions between two stars can create unusually stable zones rich in asteroids and cometary material, having gathered there over billions of years like dust in the corner of a room. This makes them veritable treasure troves for mining operations. Furthermore, the energy potential is staggering. Imagine a hub station positioned between two stars, its surface covered in solar collectors soaking up energy from two suns, generating power not just for its own operations but for beaming to outposts and ships across the local region. This abundance of cheap, sustainable energy could make such a system the industrial forge of its sector, attracting manufacturing and refining operations that are too power-intensive for a single star system to support economically. Building this infrastructure from scratch in a new star system is a challenge that demands a complete rethinking of construction. We can't send a crew of thousands or haul millions of tons of material from Earth. The journey is too long and the cost too high. The solution is to send the architects instead of the bricks. The first wave to any new system will be autonomous factory ships, vessels filled with nothing but advanced 3D printers, robotic assemblers, and swarms of mining drones. These robotic pioneers will land on resource-rich moons or asteroids and begin the patient work of bootstrapping an industrial base. They'll mine local regolith for metals, extract water ice for fuel and life support, and use solar energy to power their printers, slowly fabricating the components of a space dock one girder and one pressure hull at a time. This method of in situ resource utilization turns the destination itself into the construction yard. The historical parallels to earthly trade hubs are striking and instructive. Consider Singapore, a small island with few natural resources that grew into a global economic powerhouse solely because of its strategic location along the vital shipping lanes between the Indian and Pacific Oceans. A future hub in the Alpha Centauri system would play an identical role, a necessary stopover point that thrives on providing services refueling, repair, data exchange, and financial clearing to the traffic flowing through it. Its economy wouldn't be based on what it extracts from its own world, but on the taxes and fees it levies on the commerce it facilitates, becoming a wealthy, neutral ground where the rules of trade are enforced and disputes are settled. This centralization of trade will inevitably make these hubs the cultural and political hearts of their regions. They will be melting pots on an unimaginable scale, places where the artistic trends, philosophical ideas, and technological innovations from different branches of humanity cross-pollinate. A musical style evolving independently for decades on a colony around Barnard's star could find a new audience in the bustling markets of a Proxima Centauri hub, merging with local traditions to create something entirely new. This constant exchange will be the lifeblood of a truly galactic culture, but it also carries the seeds of conflict. Control of a major hub grants immense soft power. The entity that manages the flow of goods and information can subtly shape the development of entire star systems, potentially leading to tensions between hub authorities and the colonies they serve, or between competing corporations vying for control of these critical choke points in the flow of interstellar commerce. But this vast network of commerce, carrying unimaginable value across light years of ungoverned space, inevitably creates a target. The same emptiness that makes interstellar travel possible also provides the perfect hunting ground for those who would prey upon it. Picture the silent approach of a modified vessel, its transponder muted and its hull coated in radar-absorbent material, drifting on a parallel course with a heavily laden freighter. It launches no missiles. Instead, it releases a cloud of micro-drones, a buzzing, decentralized swarm that descends upon the freighter like locusts, seeking to disable its sensors and communications with targeted electromagnetic pulses. This is the new face of piracy, a high-tech heist conducted in the absolute dark, where the only law is what you can enforce yourself. The challenges of securing these trade routes are as vast as the distances involved. The first and greatest hurdle is simply detection. How do you spot a potential threat when it could be hiding behind a rogue asteroid, coasting with engines cold to avoid thermal signatures, or disguised amidst the background noise of the cosmos? The time lag in communications means a ship cannot call for help. By the time a distress signal reaches the nearest patrol, years may have passed. This forces every freighter to be its own fortress, a self-reliant entity capable of identifying and neutralizing threats on its own authority. The solution lies in a multi-layered sensor suite, advanced LiDAR to map objects with laser precision, passive arrays that listen for the faintest electronic emissions, and gravitational wave detectors sensitive enough to feel the displacement of a cloaked ship maneuvering nearby. Arming these civilian vessels presents a profound legal and ethical dilemma. The Outer Space Treaty of 1967 explicitly prohibits the placement of weapons of mass destruction in orbit and on celestial bodies, but it is notoriously vague on conventional arms carried by ships. Most national governments and insurance underwriters would likely prohibit freighters from carrying overt, offensive weaponry like missiles or railguns, fearing they could escalate conflicts or fall into the wrong hands. Instead, security will focus on defensive and non-lethal systems. Imagine powerful directional EMP emitters designed to fry the electronics of an approaching drone swarm, or dazzling laser arrays that can blind optical sensors without causing physical destruction. The most effective measure might be a robust point defense system, originally designed to vaporize micrometeoroids, recalibrated to target and eliminate incoming projectiles or boarding craft with pinpoint accuracy. The digital frontier is equally vulnerable. A freighter's AI is its brain, and a sophisticated cyber attack could be more devastating than any physical assault. A hacker could theoretically take remote control, commandeer the navigation system to divert the ship to a pirate rendezvous point, or simply shut down life support to force a surrender. Protecting against this requires a level of cybersecurity that makes current financial networks look primitive. We're talking about air-gapped systems with no permanent connection to external networks, communication protocols encrypted with quantum key distribution that are physically impossible to break, and AI sentries that constantly monitor the ship's own neural network for any anomalous code or attempted intrusions, ready to quarantine and purge threats in milliseconds. This new threat environment is why experts like security analyst General Maria Rodriguez are already advocating for the eventual creation of a coordinated galactic security patrol. This wouldn't be a centralized military, but a consortium-funded force operating under a strict mandate, similar to international coast guards. Their swift, well-armed cutter-style ships would patrol the busiest space lanes near major hubs, providing a visible deterrent and a rapid response force. They could investigate distress beacons, inspect vessels for compliance with safety and anti-piracy regulations, and serve as the first line of defense for the interstellar economy. Their presence would be a necessary prerequisite for attracting the massive investment required to build these trade routes, as no one will finance a cargo that can be stolen with impunity. We have a powerful historical blueprint for this challenge in the centuries-long fight against maritime piracy. The strategies that eventually secured the world's oceans convoy systems for high-value shipments, establishing recognized shipping lanes, creating international agreements for hot pursuit of pirates, and deploying naval task forces to high-risk areas will all be adapted for the cosmos. A freighter traveling alone through a sparsely populated region of the solar system is a sitting duck, but one traveling in a convoy with two others, and perhaps even a dedicated escort vessel, presents a much harder target. Insurance premiums would reflect this, creating a powerful financial incentive for collective security. The lesson from Earth is clear: security cannot be an afterthought. It must be baked into the very design of the trade network from the beginning. The most complex question of all revolves around the rules of engagement. What laws govern the use of force in the interstellar void, where no nation has jurisdiction? If a freighter's AI determines an approaching ship is a hostile threat, does it have the legal and ethical authority to fire a warning shot, or even to disable the vessel? Most agreements would likely establish strict protocols, a series of escalating challenges and warnings, the deployment of non-lethal deterrents, and the use of disabling force only as an absolute last resort to protect the lives of the crew and the integrity of the cargo. Every action would be meticulously recorded by the ship's black box, to be reviewed by the Galactic Economic Authority years later when the incident report finally reaches them. This creates a framework where captains and AIs are granted the autonomy to defend themselves, but are held to a high standard of accountability for their decisions, ensuring that the vast freedom of space does not descend into a lawless frontier. Now consider the immense challenge facing an insurance underwriter tasked with pricing a policy for the freighter Starlight Mariner on its maiden voyage to Barnard Star. The vessel itself is a masterpiece of engineering, but its journey will take 50 years one way through a void filled with unknown perils. How do you calculate a premium for that? The actuarial tables used for ocean-going ships or even orbital launches are utterly useless here. This isn't just a new market, it's a complete reinvention of risk assessment, forcing the development of financial instruments and protective frameworks as advanced as the starships they aim to safeguard. The entire economic viability of interstellar trade hinges on solving this puzzle, because without a way to confidently underwrite these missions, the required capital will simply never materialize. The first step for these future galactic insurers is data, and lots of it. They won't be relying on historical loss records, they'll be commissioning it. Before a single freighter is insured, a fleet of autonomous scout probes will be sent along the proposed trade route. These pathfinders won't just map the stars, they'll be risk assessment drones, meticulously cataloging cosmic weather patterns from unpredictable stellar flares, charting the density of micrometeoroid clouds in the interstellar medium, and identifying gravitational anomalies from rogue planets or dark matter concentrations. This data becomes the foundation of sophisticated probability models, creating dynamic hazard maps of the galaxy. The premium for a trip through a relatively calm region of space might be vastly different from one that skirts a newly formed neutron star pumping out lethal radiation. Insurers will essentially be selling security based on the quality of their celestial cartography. The range of insurance products will be as unique as the risks themselves. Standard cargo insurance will be paramount, covering the unimaginable value of the ships manifest against physical loss or damage. But then there are more exotic policies. Delay insurance will be critical. If a freighter is forced to make a lengthy course correction to avoid a cosmic storm, arriving years later than planned, the colony that ordered the cargo could face collapse. This policy would pay out for the economic losses incurred by the delay. Then there's liability insurance for environmental contamination, covering the catastrophic costs if a ship accidentally introduces an invasive microbe to a pristine exoplanet or brings an alien pathogen back into our solar system. The underwriting for each of these policies will require a deep collaboration between astrophysicists, engineers, and biologists to even comprehend the potential scenarios. The mind-bending timescales involved introduce a problem unlike any other in finance, the relativistic claims process. Imagine a ship suffers a catastrophic engine failure halfway to its destination. It takes 25 years for the distress signal to reach the insurer back on Earth. By the time an investigation team could be sent another 25 years, the ship would be a 50-year-old cold wreck. How do you verify a claim when the evidence is a half-century old and light years away? The solution will lie in absolute tamper-proof transparency. This is where decentralized technologies like blockchain become indispensable. A freighter's entire operational data, every system status, navigation decision, and external sensor reading would be hashed and recorded on a distributed ledger in real time. This creates an immutable, time-stamped record of the entire voyage. When a claim is finally received decades later, the insurer can audit this perfect digital log to verify exactly what happened, eliminating fraud and streamlining a process that would otherwise be impossible. Given the astronomical sums involved, a single freighter and its cargo could be worth more than the gross domestic product of a small nation. No single company could shoulder the risk alone. The model will inevitably be one of international risk pools, much like how major disasters are insured today. Consortiums of the world's largest reinsurers would band together to spread the exposure across the global financial system. A portion of the risk might even be securitized and sold on capital markets as exotic investment vehicles, allowing pension funds and other institutional investors to take a small slice of the risk in exchange for a piece of the premium stream. This spreading of risk is the only way to make these missions insurable, transforming a potential company-killing loss into a manageable dip in a vast, diversified portfolio. The industry isn't waiting for the future to arrive, it's actively preparing for it today. Renowned institutions like Lloyd's of London already have dedicated syndicates researching and underwriting satellite launches and orbital operations, gaining invaluable experience in the unique challenges of the space environment. This nascent space insurance market is the testing ground for the models, contracts, and expertise that will one day be scaled up for interstellar journeys. They are already grappling with issues of launch failure, orbital debris collision, and satellite longevity, providing a crucial learning curve for the vastly more complex world of interstellar coverage. Their work proves that the financial infrastructure is already evolving in tandem with the technology, ensuring that the economic framework will be ready when the first Starship is. Beyond the platinum and data chips lies a cargo of far greater subtlety yet profound impact, the cultural soul of a species. Imagine a sealed, climate-controlled container aboard the Starlight Mariner, its contents not machinery or microbes, but a carefully curated collection of artifacts from a world its recipients may never see again. Inside rests a digital archive of every major Earth language, a library of films and music spanning centuries, high-fidelity replicas of great works of art, and the sacred texts and ritual objects of 100 faiths. This is not a simple delivery. It is a lifeline, a deliberate effort to preserve the sprawling, chaotic, beautiful tapestry of human culture across the unimaginable gulf of interstellar space. The freighters become more than merchants. They transform into flying libraries, museums, and cathedrals, carrying the collective memory of humanity to its farthest outposts. This process of cultural diffusion, facilitated by the slow, deliberate rhythm of cargo ships, will fundamentally shape the societies that emerge on distant worlds. In the early, fragile years of a colony, cut off from Earth by decades of communication lag, these regular shipments of cultural data will provide a vital anchor to humanity's shared heritage. Settlers on a world-orbiting Barnard star will teach their children using textbooks and educational programs shipped from Earth, ensuring that the fundamentals of mathematics, history, and science remain consistent across the light years. Their evenings might be spent watching the same classic films and television shows that are popular back in the solar system, creating a strange, delayed shared experience. This constant, if delayed, drip feed of Earth's cultural output will help prevent the kind of radical cultural drift that could, over centuries, make colonies feel completely alien to one another. As sociologist Dr. Anya Sharma notes, this isn't about imposing Earth's culture. It's about providing a common foundation, a shared starting point from which each colony can then evolve in its own unique direction, informed by its new environment and experiences. The most fascinating outcome will be the inevitable rise of hybrid cultures. A colony on a high-gravity world might develop a more deliberate, physically conservative form of dance, which they then blend with the musical traditions of Earth to create an entirely new art form. Their language, while rooted in the English or Mandarin shipped from Earth, will gradually incorporate new vocabulary to describe their unique flora, fauna, and social structures. They might celebrate traditional Earth holidays, but adapt the rituals to their new seasonal cycles and agricultural calendar. The freighters will then carry these new cultural products back towards the solar system and to other colonies, creating a feedback loop of creative exchange. A musical style born on Proxima Centauri b could, decades later, become a surprise trend on Earth, and vice versa. This slow-motion cultural conversation, conducted through the exchange of freight, will enrich all of humanity, creating a galactic culture of stunning diversity that is still recognizably, wonderfully human. Yet, this exchange is not without its potential for conflict. The very act of curating what gets sent on these invaluable cargo runs involves immense and unconscious bias. Which Earth cultures will be deemed important enough to preserve? Which languages, which religions, which artistic movements will be allocated precious mass and volume on a freighter's manifest? A colony founded primarily by one cultural group might primarily receive artifacts reinforcing that heritage, potentially sidelining the contributions of others. Furthermore, the values encapsulated in shipped media might clash sharply with the practical realities of colonial life. A hyper-individualistic ethos common in some Earth entertainment might be dangerously at odds with the collectivist cooperation necessary for survival on a harsh new world. These shipments could become a source of generational tension, with older settlers clinging to the Earth they remember and younger generations, born on the New World, viewing these artifacts as interesting relics from a distant past rather than a living heritage. The historical parallel is the ancient Silk Road, a network of trade routes that for centuries connected the East and West. While famously moving silk, spices, and porcelain, the Silk Road's most enduring export was ideas. Religions like Buddhism spread from India to China, technologies like papermaking moved from China to the Islamic world, and philosophical concepts were exchanged and debated. The caravans carried not just goods but knowledge, art, and belief systems, fundamentally shaping the civilizations along the route. Interstellar freight routes are poised to become the Silk Roads of the galaxy, facilitating a similar exchange on a cosmic scale. The time delay adds a fascinating filter. Ideas cannot spread virally in real time, but must be physically carried, considered, and intentionally shared, perhaps leading to more deliberate and thoughtful cultural integration. For the individual living in an isolated asteroid mining outpost or on a frontier colony planet, these cultural shipments will be far more than entertainment. They will be a crucial pillar of identity and mental well-being. The ability to access a vast library of Earth's literature, to listen to music from home, or to participate in a virtual reality tour of a terrestrial museum can combat the profound sense of isolation and homesickness. Religious items allow for the practice of faith, providing comfort and community in a hostile environment. This connection to the broader human story fosters a sense of belonging to something vast and enduring, mitigating the psychological pressure of living on the edge of the known universe. The freighters, therefore, carry the emotional sustenance necessary to maintain healthy, resilient communities light years from their point of origin, ensuring that humanity's expansion does not come at the cost of its humanity. Ultimately, this dimension reveals that the cargo manifest of an interstellar freighter is a philosophical document. It represents a conscious decision about what defines us as a species and what is worth preserving as we scatter to the stars. Every gram allotted to a data chip containing a symphony or a digital copy of a masterpiece is a statement of values, a belief that civilization is built not only on fusion reactors and genetic libraries, but on beauty, story, and shared meaning. The economic narrative of interstellar trade is compelling, but it is this cultural dimension that adds the profound depth, transforming the story from one of mere commerce to one of legacy. It shows us that these vessels carry the most precious cargo of all, the collective soul of humanity, ensuring that no matter how far we travel, we never lose sight of who we are. Perhaps the most profound legacy of the interstellar freighter won't be the wealth it delivers, but the revolutionary technologies it forces us to invent along the way. The relentless demands of a decades-long voyage through the void will act as the ultimate crucible for innovation, forging breakthroughs with the power to transform life right here on our home planet. The very systems designed to keep a tiny, isolated crew alive for a generation could become the blueprint for solving some of Earth's most pressing environmental challenges. Picture the freighter's sophisticated life support system, a marvel of closed-loop engineering where every drop of water is endlessly purified. Every molecule of carbon dioxide is scrubbed and converted back into breathable oxygen, and organic waste is efficiently processed into nutrient-rich fertilizer for onboard hydroponic farms. This isn't just a spaceship system, it's a perfectly sustainable, self-contained ecosystem. Scaled up, this technology could provide the model for creating completely self-sufficient ecologies in our most overpopulated megacities, or for restoring damaged environments by establishing new, balanced ecological cycles from the ground up. The quest to protect delicate cargo and human crews from the relentless hail of cosmic radiation will drive a revolution in materials science. To shield its precious contents, a freighter's hull might be layered with new metamaterials, artificial structures engineered at the atomic level to deflect or absorb high-energy particles. These same materials, once developed, could find immediate and life-saving applications on Earth. Imagine a new generation of medical imaging machines, like MRI and CT scanners, that use this advanced shielding to drastically reduce stray radiation exposure for patients and technicians, making diagnostic procedures even safer. Or consider their use in securing hazardous nuclear waste, providing a containment so robust it could safely isolate toxic materials for millennia. The problem of protecting a starship from the harshness of space could directly lead to better protection for humanity right here at home. The artificial intelligence required to serve as the autonomous captain of a starship represents another monumental leap. This isn't a simple navigation app. It's a system that must process immense volumes of data from thousands of sensors, predict system failures months in advance, and make critical, irreversible decisions without any human input for years at a time. The machine learning algorithms developed for this purpose will be orders of magnitude more sophisticated than anything we have today. The spin-offs from this research will cascade into countless terrestrial industries. The same predictive maintenance algorithms that keep a fusion reactor running smoothly for 50 years could be applied to prevent failures in our power grids or industrial machinery. The advanced perception and decision-making systems that allow a freighter to navigate an asteroid field autonomously could provide the final key to unlocking safe, fully self-driving cars and cargo ships, revolutionizing global transportation and logistics. This wave of innovation won't happen in a vacuum. It will be fueled by unprecedented collaborations between national space agencies and the private sector. We're already seeing the blueprint for this with NASA, a commercial lunar payload services program, and its partnerships with companies like SpaceX and Blue Origin. For interstellar ambitions, these partnerships will deepen into vast consortia. A government space agency might fund the basic research into a high-risk, high-reward propulsion concept, while a private aerospace firm develops it into a working engine. A major tech corporation could provide the advanced computing hardware and AI software, and a logistics giant like Maersk or DHL would contribute its centuries of expertise in global supply chain management to design the cargo handling and distribution systems. This fusion of public vision and private sector efficiency is the engine that will drive this progress, ensuring that the astronomical research and development costs are shared and that the resulting innovations diffuse into the commercial market as quickly as possible. The historical precedent for this kind of beneficial technological fallout is powerful. The Apollo program, while focused on a single goal, gave the world a stunning array of spin-offs that now seem mundane: cordless power tools, memory foam mattresses, freeze-dried food, and even the CMOS image sensors that are now in every smartphone camera. The challenge of getting humans to the moon acted as a forcing function for innovation across computing, materials, and nutrition. The challenge of interstellar freight is exponentially greater, and so too will be the resulting cascade of new technologies. The energy required is a prime example. Developing a compact, reliable fusion reactor for propulsion could be the breakthrough that finally provides humanity with a limitless, clean source of power, ending our dependence on fossil fuels and altering the global energy landscape forever. The advanced energy storage systems needed to weather long periods without sunlight near the outer planets could lead to batteries with vastly greater capacity and longevity, solving the intermittency problems of solar and wind power and accelerating the transition to a fully renewable grid. These innovations will create massive economic opportunities long before the first freighter turns a profit. The companies that pioneer these technologies will own intellectual property with applications in dozens of terrestrial markets. A firm that develops a superior radiation shielding material for spaceship hulls could also become a leading supplier to the medical and nuclear industries. A startup that perfects a new energy-efficient water recycler for astronauts could find a ready market in drought-stricken regions and water-conscious municipalities. The research and development itself will create a new generation of high-tech jobs, attracting the best and brightest minds to work on problems that push the boundaries of science and engineering. This demonstrates the broader, more immediate value of the endeavor. The pursuit of interstellar freight isn't just an investment in a distant future, but a powerful catalyst for progress that will deliver tangible benefits to our global society within our own lifetimes, proving that the road to the stars is paved with innovations that improve life on Earth every step of the way. Yet this monumental undertaking demands a financial engine of equally staggering proportions, one capable of funding endeavors where the first returns on investment may not materialize for half a century or more. The capital required to construct a single interstellar freighter, along with its supporting infrastructure, would likely reach into the trillions of dollars, a sum so vast it cannot be shouldered by any single government or corporation. This forces us to invent entirely new models of investment and funding, structures designed for a timescale that dwarfs human lifespans and a risk profile that includes cosmic uncertainties. The solution will likely be a layered, hybrid approach, blending the cautious stability of public institutions with the aggressive innovation of private capital and the democratic power of the global public. One of the most compelling possibilities is the rise of micro-investment on a galactic scale. Imagine a global crowdfunding campaign for the first freighter, a project backed not by billionaires, but by millions of ordinary people purchasing symbolic shares for a few dollars each. This wouldn't just be about raising capital, it would be about fostering a sense of shared ownership in humanity's future among the citizens of Earth. A person might buy a share to have their name etched on a plaque aboard the ship, or to include a family photo in its digital archive, creating a personal, emotional stake in the mission's success. While the individual financial return would be minuscule and distant, the psychological return, the pride of participation in a historic leap for our species, would be immediate and profound. This model democratizes the grandest ambition, transforming it from a project of the elite into a collective human enterprise. For the immense foundational investments, the model of public-private partnerships, proven by projects like the International Space Station, will be indispensable. Government space agencies like NASA or the European Space Agency would play a crucial role in de-risking the initial technologies. They might fund the basic research into advanced propulsion systems or life support, proving the concepts at a prototype level. Once the fundamental viability is established, private entities could then step in to refine the technology for commercial production and operation. A government might contract a company to build the first space dock at a Lagrange point, effectively creating an anchor tenant and a stable revenue stream that justifies the private sector's massive capital expenditure. This partnership allows the public sector to set strategic goals and ensure safety, while leveraging the private sector's efficiency and drive for innovation. Venture capital will also find its place, though it will operate on a far longer horizon than the typical 10-year fund cycle. Visionary venture firms specializing in deep future investments would back the high-risk, high-reward startups developing the core enabling technologies, the specialized robotics for autonomous repair, the novel metamaterials for radiation shielding, or the AI architectures for long-duration command. Their payoff wouldn't come from the freighter itself, but from the lucrative licensing of these breakthrough technologies for terrestrial applications. The advanced water recycler developed for a starship could revolutionize conservation in arid regions, and the ultra-reliable battery designed for the dark cruise between stars could transform renewable energy storage on Earth. The venture model here bets on the spin-off, not the primary mission. The most complex financial innovation will be the development of long-duration interstellar bonds. As leading space economist Dr. Ben Carter theorizes, these would be century-length bonds, essentially loans made to a freighter project that only mature upon the ship's successful arrival and data transmission from the destination system. The bond's value wouldn't be in regular interest payments, but in a massive final payout based on the verified value of the information and resources acquired. To make these bonds palatable to institutional investors like pension funds or sovereign wealth funds, they would need to be backed by solid collateral. Dr. Carter's concept of resource-backed loans is particularly ingenious here. The entity building the freighter could use the prospecting rights to a specific, resource-rich asteroid in our solar system as collateral for the bond. This gives investors a tangible, valuable asset to underwrite the risk, ensuring that even if the interstellar mission itself fails, the bondholders have a claim on a nearby celestial asset that can be developed to recoup their investment. This entire ecosystem would necessitate a new forum for exchange, a dedicated galactic stock market. This wouldn't be a physical trading floor, but a digital, decentralized exchange operating across the solar system, listing shares in everything from freighter lines and mining consortia to the insurance pools that underwrite them. The extreme time delays would make rapid trading impossible, shifting the focus toward long-term value investing based on meticulously vetted data packets that arrive from distant hubs every few years. The value of a stock would hinge on the contents of these periodic reports, a confirmed discovery of a rich platinum deposit by a mining subsidiary, or the successful establishment of a new agricultural colony on an exoplanet. Trading would be a deliberate, strategic affair, more akin to managing a multi-generational trust fund than the high-frequency frenzy of modern markets. We can already see the precursors of this model in the funding of modern space companies. SpaceX, for instance, has masterfully blended revenue from government contracts for cargo and crew missions to the International Space Station, with massive injections of private equity from investors betting on its long-term vision of Martian colonization. This mix of guaranteed government work and speculative private investment provides the stable capital needed to develop foundational technologies like reusable rockets, while also funding the more ambitious, forward-looking research into systems like Starship. This approach demonstrates the essential template: use near-term, practical contracts to fund the development of the capabilities that will eventually enable the long-term, transformational goals. The journey to the stars will be paid for one delivery at a time, with each successful contract building the credibility and capital needed for the next, greater leap into the unknown. To truly grasp the timeline ahead, we need to see our current moment not as a beginning, but as a point on a continuum of exponential progress. Cast your mind back to 1957, when Sputnik's faint beep signaled humanity's first tentative step into the cosmos. That was just over 60 years ago. In that relatively brief span, we've progressed from that simple satellite to reusable rockets landing themselves on drone ships, and to a constant human presence aboard the International Space Station. This acceleration suggests that the next 100 years will contain leaps far greater than the last. The journey to interstellar freight isn't a single giant leap. It's a marathon of sequential sprints, each one building on the last. Based on the current technological trajectory and consensus from leading research institutes like Oxford's Future of Humanity Institute, we can map a realistic, though ambitious, forecast. The mid-21st century, around 2050, is when we'll see the true birth of a space economy, but it will be local. This is the era of inner system trade. The first major milestone will likely be the opening of the first profitable asteroid mine, perhaps targeting a water-rich carbonaceous asteroid to supply orbiting fuel depots. We'll see regular traffic between Earth and Mars, not just with astronauts but with specialized cargo haulers transporting refined metals, manufactured goods from orbital factories, and critical volatiles. This period is about building the industrial muscle and logistical frameworks right here in our celestial backyard, proving the economic models that will later be scaled up for the stars. The turn of the next century, around 2100, marks the pivot point from interplanetary to interstellar. This is the era of the robotic pathfinder. While inner system commerce hums along, we will launch the first dedicated interstellar probes. These won't be the tiny, laser-pushed wafers of breakthrough starshot, but larger, more capable vessels, perhaps utilizing advanced nuclear fusion propulsion. Their mission, detailed reconnaissance of our closest stellar neighbors, like the Proxima Centauri system. Their arrival and data return will be the most awaited event in human scientific and economic history, providing the first truly reliable assessment of which exoplanets are not just habitable but profitable. The discovery of a single, truly Earth-like world with confirmed biosignatures and abundant resources would instantly electrify the global economy, shifting trillions of dollars in investment toward making the next step a reality. This sets the stage for the 22nd century, around 2200, for the dawn of true interstellar freight. This is when the first purpose-built, automated cargo vessels, constructed in the zero-gravity shipyards of the asteroid belt, will begin their long journeys. Their design will be finalized based on a century of operational data from inner system freighters and the detailed reports from the interstellar probes. Their initial cargoes will be exactly what we've discussed: high-value, low-mass seeds of civilization. This timeline aligns with the prediction of visionary physicist Freeman Dyson, who famously speculated that interstellar travel would be achievable within 200 years of its first serious consideration, which places his deadline around the year 2160. Our forecast is perhaps more conservative, acknowledging the sheer scale of the engineering challenges, but it sits comfortably within the same century. Of course, this timeline is a projection, not a prophecy. Its pace hinges entirely on a series of potential breakthroughs that could act as powerful accelerants. The sudden achievement of sustainable, net-positive fusion energy here on Earth would pour virtually limitless cheap power into the global economy, freeing up immense resources for space development. A major discovery in fundamental physics that brings a concept like the Alcubierre warp drive from the realm of mathematical curiosity into the realm of engineering possibility would collapse the timeline overnight. Conversely, delays are just as possible. A global economic depression, a prolonged period of international conflict that diverts resources and cooperation, or a major catastrophe in space that sets back public and political will could add decades to each of these milestones. The timeline is a function of our collective focus, investment, and will. Understanding this potential pace is crucial for more than just setting expectations. It's a guide for action. It tells today's researchers which long-term problems need solving now. It tells investors where to place patient capital. It tells policymakers what international treaties and frameworks need to be developed to prepare for this future. It tells educators what skills the next generation will need to build this reality. By visualizing the path from the first satellite to the first interstellar bill of lading, we make the incredible seem incremental, the impossible seem inevitable. We transform a dream of the far future into a series of solvable engineering challenges, each one bringing that distant glimmer of a galactic economy one step closer to reality. The story of the SS Pioneer transforms our theoretical exploration into a tangible, gritty reality, a mission that forever changed our perception of what was possible. Conceived not as a vessel of exploration but as a practical, profit-driven endeavor, its target was the Tau Ceti system, selected after decades of painstaking analysis. While closer stars like Proxima Centauri were nearby, Tau Ceti's sun-like star and the confirmed presence of multiple planets within its habitable zone made it the most promising candidate for a fledgling colony, a potential customer worth the extra travel time. Its cargo manifest was a masterclass in applied interstellar economics, not bulk ore but a suite of compact, self-replicating nanofabricators, a complete cultural and scientific database etched onto diamond-solid data chips, and a sealed biostorage unit containing thousands of seeds and microbial cultures specifically engineered for the predicted conditions of Tau Ceti. This was a civilization starter kit, a single shipment designed to catapult a potential outpost from survival to technological sovereignty. Mission Director Dr. Chloe Park, whose team spent years running simulations at the Interstellar Logistics Institute, often emphasizes that their greatest challenge wasn't the technology, but the psychology of the timeline. The Pioneer was launched with the understanding that its one-way journey would take just over 112 years. The investors funding the mission, a consortium of lunar mining corporations and tech giants, were not individuals but trusts and legacy funds, their prospectuses clearly stating that returns were intended for the grandchildren of the initial backers. The crew, a carefully selected team of 12, signed contracts knowing they would never see Earth again, that their entire lives would be spent maintaining the ship for a future they would only glimpse upon arrival. Their commitment was to a legacy, not a paycheck, a mindset that had to be rigorously tested and reinforced during their decade of training. The voyage itself was a relentless test of the ship's autonomous systems and the crew's resolve. 2 decades into the journey, the Pioneer encountered the first major crisis, a cascade failure in its primary navigation array, caused by a micrometeoroid impact too small for the point defense systems to intercept. For 72 hours, the ship was effectively blind, drifting on its last known trajectory while the 3 independent AI cores argued over the correct repair protocol. It was the human crew chief, engineer Kaito Tanaka, who made the critical decision. He overrode the eye's deadlock, donned a pressurized exosuit, and led a team outside to physically replace the damaged sensor cluster with a unit fabricated from onboard reserves. This event became a cornerstone case study, proving that while AI could manage 99.9% of a mission, human intuition and courage were irreplaceable for that critical 0.1%, the unforeseen anomalies that no simulation could ever predict. After a century of travel, the moment of arrival was anticlimactic in its silence. The Pioneer decelerated into the Tau Ceti system, its powerful scanners immediately confirming the presence of a thriving, if still primitive, human colony on the 4th planet. The initial survey probes had been right. The world was habitable, and a generation ship from a rival consortium had arrived 40 years prior, establishing a beachhead. The Pioneer's cargo, however, was exactly what the struggling colony desperately needed. The nanofabricators allowed them to move beyond basic subsistence, creating advanced tools and medical equipment from local materials. The cultural archives provided a vital link to Earth, preventing drastic cultural drift, while the tailored crops dramatically increased agricultural yields. The Pioneer itself, its fusion reactor and hull, became the cornerstone of the colony's first orbital space dock, a permanent monument to its origin. The economic impact resonated back across the light years, though the data took 12 years to reach Earth. The success of the Pioneer mission validated the entire economic model of interstellar freight. The data sold by the Tau Ceti colony, detailed geological surveys, atmospheric analyses, and biological findings was purchased for a sum that repaid the initial investment many times over and provided a treasure trove of information for future missions. More importantly, it created a tangible link. The Tau Ceti system was no longer a point of light in a telescope. It was a trading partner. The lessons learned from the Pioneer's navigation era led to a redesign of sensor arrays on all subsequent freighters, and the heroics of its crew informed new training protocols, emphasizing adaptive problem-solving over rigid procedure. The mission proved that interstellar trade was not a fantasy, but a difficult yet achievable engineering and economic challenge, paving the way for the bustling galactic economy that would follow. This delicate dance between public oversight and private ambition is already playing out in our own celestial backyard, offering a preview of the power struggles to come on an interstellar scale. Picture the tense atmosphere in a conference room aboard a spinning station at the Earth-Moon Lagrange Point 1. On one side of the table sit representatives from the United Planetary Consortium, a body formed by several national governments. Across from them are the sharply dressed executives of Stellaris Freight, the largest private shipping conglomerate. The issue at hand is a simple yet profoundly powerful one: docking rights and fee structures for the newly completed Proxima Centauri trade hub. The government officials argue for regulated, standardized fees to ensure access for all, including scientific and cultural missions that may not turn an immediate profit. Stellaris counters that their massive private investment in the hub's construction grants them the right to prioritize their own vessels and set market-rate prices, arguing that this efficiency is what makes the entire enterprise viable. This isn't just a business negotiation, it's a fundamental debate over who controls the gateway to another star system, setting a precedent that will echo for centuries. Governments are poised to play a role reminiscent of their historical part in regulating other great infrastructure projects like railroads or telecommunications networks. Their primary functions will be threefold: providing the initial high-risk capital for foundational research, establishing and enforcing a legal and safety framework, and ensuring security along the space lanes. The development of the first fusion drive prototypes or the construction of the initial Lagrange point shipyards will require investments so vast and with such distant returns that only public treasuries, acting through agencies like a future-evolved NASA or a new interstellar development organization, can shoulder the initial burden. Once the basic technology is proven, governments will then need to act as referees, creating the rulebook for this new game. This means establishing standards for spacecraft construction to prevent catastrophic accidents, setting planetary protection protocols to avoid biological contamination, and forming a legal framework for resolving disputes that arise between entities light years apart. Finally, just as navies have historically protected maritime trade routes, a publicly accountable security force will likely be necessary to patrol the space lanes between major hubs, deterring piracy and ensuring that commercial competition doesn't escalate into corporate warfare in the void. Private enterprise, on the other hand, will be the engine of innovation and efficiency, driven by the powerful incentives of competition and profit. Companies like a future incarnation of SpaceX or entirely new entities will excel at taking the foundational technologies developed with public funds and refining them for commercial use, driving down costs through relentless innovation and economies of scale. Their focus will be on optimizing every aspect of the operation, from designing more fuel-efficient engines and faster loading processes to developing the sophisticated AI logistics software needed to manage a supply chain with decades-long delays. This competition between private firms will be the primary force that lowers the cost of interstellar transport, eventually making it accessible to more than just governments and the ultra-wealthy. The history of the satellite launch industry is a perfect microcosm. Before private competition entered the field, launch costs were prohibitively high. The entrance of companies driven by market forces dramatically reduced prices and increased launch frequency, a pattern we can expect to see repeated on a galactic scale. The model for a successful partnership is already being written. NASA commercial crew and cargo programs, which contract with private companies like SpaceX and Northrop Grumman to resupply the International Space Station, provide a brilliant blueprint. The government agency sets the high-level safety and mission requirements and acts as the anchor customer, providing a stable revenue stream. Private companies then compete to meet those goals in the most cost-effective and innovative way possible. This model leverages the bureaucratic stability and long-term vision of government with the agility and efficiency of the private sector. We can easily envision this scaling up, with a Galactic Trade Commission hiring private freight lines to establish supply routes to new colonies, ensuring these outposts survive and thrive while simultaneously fostering a competitive commercial space industry. However, the risks of a system tilted too far toward corporate power are starkly illustrated by history. The British East India Company serves as a sobering cautionary tale. What began as a trading company eventually became a de facto colonial government, with its own private army, exercising sovereign power over millions of people for profit. In an interstellar context, a massively powerful corporation that controls the only efficient freight line to a fledgling colony could hold that colony hostage, demanding exorbitant prices for essential goods or even influencing its governance. Without public oversight, the galactic economy could create terrifying new paradigms of inequality, where the wealth and opportunities of the stars are available only to those on planets owned or favored by the major corporations, while other worlds are left as isolated backwaters. Resolving the inevitable conflicts of interest will require the creation of new, neutral institutions with interstellar authority. Disputes over mining rights to a lucrative asteroid in the Alpha Centauri system cannot be adjudicated by a court in a single nation on Earth. This will likely lead to the formation of a galactic economic authority, as mentioned by experts like Dr. Rajiv Mehta, a transnational body with the power to regulate trade, arbitrate disputes, and enforce safety and environmental standards. Its authority would be derived from treaties signed by participating planetary governments and major corporations, who would agree to abide by its rulings because the alternative, a lawless, unpredictable free-for-all, is bad for business and for civilization in the long run. This body would ensure that the incredible power of interstellar commerce serves to uplift all of humanity, preventing our greatest achievement from becoming a new frontier for exploitation and inequality. The balance struck between these forces will determine whether the galactic economy becomes a shared human project or a divided empire of corporate fiefdoms. This evolution from simple supply lines to a complex galactic economy begins with the very infrastructure the freighters help create. Those initial shipments of nanofabricators and industrial replicators are designed for one purpose: to allow a colony to bootstrap its own manufacturing capability. A freighter doesn't just deliver a load of microchips, it delivers the machine that can make the microchips using raw materials mined from local asteroids. This transforms the colony from a passive consumer of imported goods into an active producer, capable of meeting its own basic needs and eventually creating unique exports tailored to its environment. A planet with low gravity might specialize in producing vast, delicate crystal structures for advanced optics, impossible to manufacture on Earth. A colony orbiting a metal-rich star might become a hub for smelting and alloy production, its orbital factories processing ore into standardized girders for construction across the sector. The freight network's initial role as a delivery service gradually shifts towards transporting these specialized, high-value goods between established worlds, weaving a web of mutual economic dependence. This burgeoning interdependence gives rise to entirely new service industries, the soft infrastructure of a civilization. The movement of physical goods necessitates the parallel movement of capital and legal agreements, creating a booming field for interstellar finance and law. Interstellar accountants become essential, not just for managing transactions across decades of travel time, but for navigating the mind-bending complexities of relativistic finance. A payment for a shipment sent from Earth might be due upon arrival at Proxima Centauri, but due to time dilation effects, the journey might have taken 40 years for the freighter, but 41 years have passed on Earth. Calculating the interest on that investment requires a whole new form of mathematics. Similarly, exo-lawyers specialize in the intricate patchwork of inter-system trade law, resolving disputes over contracts signed by individuals who may have passed away long before the case is ever heard, and establishing legal precedents for jurisdiction in a realm where traditional borders are meaningless. As stability grows and travel becomes more routine, the economy expands beyond mere necessity into the realm of experience and luxury. The same space docks built for freighters begin to welcome very different vessels, interstellar luxury liners. These would be the pinnacle of engineering and comfort, equipped with state-of-the-art inertial dampeners and rotating sections to simulate gravity, offering wealthy tourists the vacation of a lifetime, a multi-year journey to witness the breathtaking double sunsets of a binary star system or to experience the low-gravity ballet of a resort on a Martian moon. This sector would create a host of new professions, from hospitality managers trained in long-term guest care to exobiologists leading safaris across carefully curated alien landscapes. The economy is no longer just about survival and industry. It's about catering to the human desire for wonder and exploration. Measuring the output of such a vast and diverse system requires a complete rethinking of economics itself. Traditional metrics like gross domestic product tied to a single planet become obsolete. In their place, economists develop the concept of galactic domestic product, or GDP, a measure of the total value of all goods and services produced across human-settled space. This figure would be staggering, encompassing everything from the value of data transmitted from a research outpost to the tourism revenue of a resort on Titan. More fascinating than the scale, however, is the potential shift in the very foundation of value. With access to the near-limitless resources of asteroid belts and gas giants, the concept of scarcity that has defined Earth's economics for millennia begins to crumble. Essential resources like energy, basic metals, and even food could become so abundant that their cost approaches zero. This is the post-scarcity economy that visionaries like Dr. Leo Grant have long predicted. In such a system, currency itself might transform. Instead of being backed by the arbitrary faith of a government, new inter-system currencies could be directly pegged to tangible resource standards. A solari might be defined by a specific amount of energy, say 1 megawatt-hour, or a Centauri might be backed by a gram of purified helium-3 fuel. This creates a stable, universal medium of exchange whose value is consistent across light years, because a unit of energy or fuel is the same in the Proxima system as it is in our own. The focus of human endeavor would then shift from the acquisition of basic necessities to the pursuit of knowledge, art, personal growth, and exploration. Work would be chosen for its meaning and contribution, not merely for survival. This grand expansion, built upon the humble foundation of the interstellar freighter, ultimately redefines humanity's place in the cosmos. We transition from a species confined to a single world, struggling for resources, to a galactic civilization interconnected by trade, ideas, and a shared future. The freighters that began as simple cargo carriers become the arteries of this new entity, pumping not just goods but prosperity, culture, and opportunity to every corner of our settled space. They enable a future where the measure of wealth is not what you possess, but what you can experience and create, turning the entire galaxy into a canvas for the next chapter of the human story. As we've journeyed through the vast possibilities of interstellar freight, one truth emerges with brilliant clarity. This isn't just science fiction, it's the plausible foundation of humanity's first truly galactic economy. This endeavor reaches far beyond the simple movement of goods. It represents a fundamental shift in how we perceive value, connection, and our very place in the cosmos. We've navigated the incredible engineering feats, from fusion drives that harness the power of stars to autonomous AI captains guiding vessels across light years of silent void. We've wrestled with the profound ethical questions of protecting alien ecosystems and the complex legal frameworks needed to govern trade between worlds separated by decades. And we've seen how the humble act of shipping cargo could weave together the scattered threads of human civilization into a rich, interconnected tapestry, fostering new cultures, new arts, and new ways of being human. Each challenge, from propulsion to piracy, is matched by an opportunity so vast it redefines the word ambition. The most exciting part of this entire vision is realizing that the freighters of tomorrow are not just dreams, they are being designed today. In laboratories from Tokyo to Boston, physicists are running simulations on containment fields for antimatter reactors. In Silicon Valley, engineers are coding the neural networks for the AI that will one day navigate an asteroid field. In boardrooms and at space agencies, strategists are drafting the first interplanetary trade agreements. This future is being built piece by piece, breakthrough by breakthrough, by a global community of thinkers, makers, and visionaries. You don't need to be an astronaut to be a part of this grand adventure. Perhaps you're an investor considering the long-term potential of a space mining startup, or a student studying exo-law and planetary ethics. Maybe you're a storyteller, an artist, or an engineer. Every discipline has a role to play in shaping the narrative and the reality of our expansion into the galaxy. This conversation doesn't end when this video does. We want to hear your vision for this incredible future. Look up at the night sky and tell us in the comments, if you could open trade relations with any star system out there, which one would it be and why? Would it be the promising worlds of the TRAPPIST-1 system with its 7 rocky planets, or the familiar sun-like star of Tau Ceti? Your curiosity is the first step toward making it real. If you've enjoyed this deep dive into humanity's next great chapter, make sure to subscribe and hit the notification bell. We're exploring everything from the architecture of orbital colonies to the psychology of generation ship crews, and we don't want you to miss a single discovery. Together, we're not just passive observers of the future, we are its active architects laying the groundwork for an economy that will one day span the stars.